Picture this. You're standing on the rust-red soil of Mars, gazing out across a canyon so vast it could swallow entire mountain ranges back on Earth. The sky above isn't blue but a pale, dusty pink, and the silence is absolute. No wind, no birds, just the profound stillness of an alien world. But here's what makes this moment truly extraordinary. You're not just a visitor in this otherworldly landscape. You're an explorer, equipped with technology so advanced it feels like it's straight out of our wildest science fiction dreams. Tools that let you see through rock, communicate instantaneously across millions of miles, and even build shelters from the very dust beneath your feet. This isn't some distant fantasy. This is the future of space exploration, and it's arriving faster than you might think. For centuries, humanity has looked up at the stars with a mix of wonder and curiosity, dreaming of what might lie beyond our atmosphere. We've sent probes, launched telescopes, and even walked on the moon, but we've always been limited by the technology of our time. Now, we're on the verge of something truly revolutionary. Breakthroughs in artificial intelligence, materials science, and energy systems are converging to create a new generation of space tools that will fundamentally change how we explore, understand, and eventually inhabit alien worlds. These innovations aren't just incremental improvements, they're game changers that will allow us to go further, stay longer, and discover more than ever before. In this video, we're going to dive deep into 28 of these revolutionary tools, each one more incredible than the last. From autonomous swarm rovers that work together like a colony of ants to self-healing materials that repair themselves in the harshest conditions, these technologies are reshaping what's possible in space exploration. We'll explore how quantum communication could eliminate the frustrating delays we currently face, how 3D printed habitats might let us build cities on Mars, and how fusion power could provide nearly limitless energy for our most ambitious missions. Whether you've been following space exploration for years or are just curious about where technology is taking us, this journey will open your eyes to the incredible future that's waiting just beyond our horizon. So settle in and get ready to discover the tools that will not only take us to new worlds, but will change how we see our place in the cosmos forever. Think back to the very beginning, to a time when simply reaching orbit was a monumental achievement. Those first missions were armed with little more than courage and the most basic of instruments, simple radios, rudimentary cameras, and sensors that, by today's standards, seem almost quaint. The Soviet Union's Sputnik, the first artificial satellite, was little more than a polished metal sphere with 4 radio antennas, yet its faint beep-beep-beep signal, broadcast to the world, marked the dawn of a new age. Then came the early American probes like Explorer 1, which carried a cosmic ray detector and discovered the vast belts of radiation surrounding our planet that we now call the Van Allen belts. These were tools of pure discovery, designed to answer the most fundamental questions. Can we survive up there? What is the environment actually like? This era of basic reconnaissance soon gave way to a more hands-on approach with the Apollo program. The tools became an extension of the human explorers themselves. Astronauts like Harrison Schmitt, a trained geologist, wielded modified rock hammers, tongs, and sample bags to collect the moon's treasures. The lunar roving vehicle, a marvel of engineering folded into a tiny package, expanded their range, turning a short walk into a genuine geological field trip. These weren't just instruments, they were enabling devices crafted by human hands for human hands, and they brought back a wealth of knowledge that reshaped our understanding of the solar system's history. Every sample was a puzzle piece, carefully chosen by a scientist's eye on another world. The next great leap was the shift from human-guided exploration to robotic pioneers. This was the era of the Viking landers on Mars, which didn't just take pictures. They scooped up soil and conducted the first ever biological experiments on another planet, searching for the whispers of life. The Voyager probes, armed with cameras and a suite of sensors, became our eyes and ears in the outer solar system, revealing the stunning volcanic activity of Io and the intricate rings of Saturn. These machines were more sophisticated, but they were still remote-controlled in a very direct way, with every command painstakingly sent from Earth and every byte of data eagerly awaited for hours or even days. Then everything changed with the infusion of intelligence. The Mars Pathfinder mission and its little Sojourner rover showed us a new way to explore, a mobile, interactive presence on another world. This set the stage for the truly revolutionary shift. Smart tools, rovers like Spirit, Opportunity, and Curiosity weren't just remote-controlled cars, they were field geologists on wheels. Packed with spectrometers, microscopic imagers, and rock abrasion tools, they could analyze a rock's chemistry and geology in situ. Most importantly, they gained a degree of autonomy. Their onboard computers could navigate around hazards, choose interesting targets, and even plan their own driving routes to a degree, making decisions in minutes that would take hours if they had to wait for instructions from Earth. This evolution, from simple beeping satellites to intelligent, decision-making robots, paints a clear picture. It's a story of moving from merely observing to truly interacting, from basic data collection to sophisticated analysis, and from total human control to collaborative autonomy. Each generation of tools has stood on the shoulders of the last, building a foundation of knowledge and capability. We learned what worked, what failed, and what we needed to do next. This relentless innovation, driven by that timeless human curiosity, has brought us to the threshold of today's revolution. The tools we have now aren't just better, they're fundamentally different, and they are about to change everything we know about exploring the final frontier. But what does this intelligence actually look like in action? It's not just about a rover avoiding a rock. It's about a machine understanding the scientific value of that rock in the first place. Modern rovers, like Perseverance on Mars, are equipped with AI that can analyze the landscape through its cameras, identify a specific type of geological formation, say, a particular layering in a cliff face that suggests ancient water flow, and then, on its own initiative, decide to drive over and use its laser spectrometer to zap the rock for a closer analysis. This isn't remote control, this is a robotic partner making informed scientific choices. The delay for a signal to travel from Earth to Mars can be up to 20 minutes one way, making real-time guidance impossible. Instead of sitting idle for 40 minutes waiting for a human to tell it what to do next, the rover uses its artificial brain to assess the situation, weigh its options based on pre-programmed scientific priorities, and get on with the job. This autonomy turns a single Martian day, or sol, from a slow, step-by-step process into a flurry of productive activity, dramatically increasing the scientific return on these incredibly expensive missions. The role of AI extends far beyond the surface of planets, reaching deep into the void to make sense of the universe itself. Our orbital telescopes and deep space observatories collect a truly staggering amount of data, petabytes of images, spectral analyses, and radiation readings. It is simply beyond human capacity to sift through all of this information manually. This is where machine learning, a subset of AI, truly shines. scientists train algorithms on known data, for example, the light curves of thousands of confirmed stars, and then set them loose on new datasets to find anomalies. This is how we discover the bizarre and the unexpected: exoplanets transiting distant stars, the gravitational waves from colliding black holes, or strange interstellar objects like Oumuamua. The AI doesn't get tired, it doesn't need to sleep, and it can process millions of data points in the time it takes a human to review a single image. It acts as a force multiplier for human curiosity, flagging the most intriguing needles in a cosmic haystack so that scientists can focus their limited time on the most promising discoveries. This powerful combination of autonomy and analytical prowess is also what makes future missions not just smarter, but safer and more resilient. Imagine a spacecraft landing on the icy moon Europa. The surface is treacherous, riddled with cracks and crevices. An AI-powered landing system can process real-time imagery during its descent, comparing the terrain below to hazard maps and instantly adjusting its trajectory to touch down on the safest, most stable patch of ice available. Once there, if a component were to fail, the system's AI could diagnose the problem, switch to a backup system, or even reconfigure its remaining healthy instruments to continue the mission objectives in a new way, all without a single command from home. This resilience transforms a mission from a fragile, one-shot endeavor into a robust, adaptable exploration partner. It's this invisible, thinking layer of technology that will allow our tools to not just visit these alien worlds, but to truly understand them. Now, let's take this concept of intelligent, collaborative machines and give it a physical form, starting with what might be the most transformative shift in planetary exploration: the move from the solitary, heroic rover to a coordinated, intelligent swarm. This is our first revolutionary tool: autonomous swarm rovers. Forget the image of a single, car-sized machine slowly picking its way across a lonely landscape. Instead, envision a dozen or more smaller, lighter rovers, each about the size of a microwave, tumbling out of a lander and immediately beginning to work together as a unified team. They wouldn't be identical clones, each would have a specialized role, much like individuals in an ant colony or a pack of wolves. Some would be scouts, equipped with high-resolution cameras and LiDAR, zipping ahead to map the immediate terrain in exquisite detail, identifying sand traps, large rocks, and steep inclines. Their data would be instantly shared across the swarm's network, creating a dynamic, real-time hazard map that all the others can see. Following behind would be the analysts. These rovers might carry the heavy scientific payloads, a miniaturized spectrometer on one, a drill for subsurface sampling on another, a microscopic imager on a third. Because they don't all need to carry every single instrument, each can be lighter, more energy efficient, and more agile. Guided by the Scout's data, they can fan out to investigate multiple points of interest simultaneously. Instead of a mission spending weeks driving a single rover from one rock to another, a swarm could study a dozen different geological formations within a single day, dramatically accelerating the pace of discovery. Their collective observations would provide a rich, multi-point context for the area, turning a single data point into a comprehensive understanding of an entire environment. The true genius of the swarm, however, lies in its resilience and mutual support. Imagine one of these rovers loses traction in a patch of fine, loose dust, its wheels spinning helplessly. In the old model, that could mean a mission-ending catastrophe, or at least a weeks-long delay as engineers on Earth tried to plan a complex recovery maneuver. In a swarm, other rovers would immediately detect the problem. A larger, more powerful rover designed for heavy lifting could maneuver into position and gently nudge or even pull its stranded companion free. Another rover, acting as a communication relay, could reposition itself to ensure the entire team maintains a strong day to link back to the orbiter overhead, preventing any loss of precious information. This isn't just a team, it's a self-healing network where the failure of one unit doesn't doom the mission, but simply triggers an adaptive response from the collective. This approach is perfectly suited for the most tantalizing and dangerous destinations in our solar system. Consider the icy surface of Jupiter's moon Europa, cracked and jumbled like a broken pane of glass. Sending a single, large rover there would be an immense risk. A swarm, however, could be deployed to explore this treacherous terrain. While some units might be lost into crevices, others would survive, learning from the fate of their companions and mapping out safe paths for the group to continue its exploration of the moon's mysterious surface. They could work together to lower sensors into cracks or even pool their power to operate a single, more powerful instrument. This shift from a lone explorer to a collaborative, adaptable team marks the beginning of a new philosophy in space exploration, one where redundancy, cooperation, and distributed intelligence replace the fragility of a single, monolithic machine. But having a team of intelligent scouts is only half the battle. The ultimate goal is to stay, and that means building a home. This brings us to our second revolutionary tool, 3D printed habitat construction systems. For decades, the vision of a Martian base or a lunar outpost was plagued by one enormous, seemingly insurmountable problem. How do you get a building there? The cost of launching even a single kilogram of material from Earth is astronomical, and the idea of shipping entire prefabricated structures with their bulky walls and fragile components was a logistical nightmare that threatened to keep us confined to short-term camps. The solution, it turns out, isn't to bring the house with us, but to bring the printer and let the planet provide the ink. This technology moves far beyond the small plastic printers you might be familiar with. These are massive robotic systems that work on an entirely different principle, known as in-situ resource utilization. Their primary building material is the very ground beneath them, the fine, gray dust of the moon known as regolith, or the iron-oxidized, rusty soil of Mars. The process is both simple and brilliant. A rover equipped with a large scoop first harvests the local soil. This material is then processed, sometimes mixed with a binding polymer brought from Earth, or in more advanced concepts, fused together using concentrated sunlight or microwaves. The printer head, mounted on a large gantry or a mobile robotic arm, then deposits this mixture layer by precise layer, slowly building up walls from the ground up according to a pre-designed digital blueprint. The structures they create are far from primitive mud huts. They are engineering marvels optimized for survival in an alien environment. The thick walls, made from sintered regolith, provide excellent protection from one of the deadliest threats in space, radiation. On Earth, our atmosphere and magnetic field shield us from constant cosmic rays and solar flares, but on the Moon or Mars, an astronaut inside a thin-walled habitat would be exposed to dangerously high levels. A 3D printed wall, several feet thick, acts as a natural radiation barrier, using the planet's own soil to keep its explorers safe. Furthermore, these printers can create complex, organic shapes that are incredibly strong. Think of the efficiency of an eggshell or an arch designs that would be impossible to transport, but are trivial to print on site, offering superior structural integrity against the stresses of a low-gravity environment or even potential meteoroid impact. But the innovation doesn't stop at the initial print job. The true genius of these systems lies in their potential for smart maintenance and dynamic growth. Imagine a habitat wall embedded with a network of tiny, fiber optic sensors that constantly monitor for microfractures caused by temperature swings or settling. If a crack is detected, a smaller repair bot, essentially a miniature version of the main printer, could be dispatched to automatically patch the damage, effectively giving the habitat a self-healing capability. And when the first crew is joined by a second, expansion is a matter of programming, not construction. The printer simply goes back to work, adding a new module, connecting a new corridor, or printing entirely new furniture from the recycled plastic of packaging materials. This transforms a base from a static, fragile outpost into a living, growing, and resilient organism, capable of adapting to the needs of its inhabitants and ensuring that our foothold on other worlds is not just temporary but permanent. Now let's tackle one of the most frustrating limitations of deep space exploration, a problem that has plagued mission planners since the very beginning: the speed of light itself. Our current method of communication relies on radio waves, which, while reliable, are painfully slow over interplanetary distances. This speed limit creates an agonizing delay. A signal traveling at the speed of light takes over 20 minutes to make a one-way trip to Mars. That means if a rover on Mars encounters a problem, it could be 40 minutes before engineers on Earth even know about it and can send a corrective command. For a mission to Jupiter's moon, Europa, that delay stretches to over an hour. This lag turns remote operations into a slow, stuttering dance, preventing any kind of real-time guidance and forcing our incredibly sophisticated robots to spend most of their time waiting. It's like trying to play a video game with a 40-minute lag between pressing a button and seeing the action on screen. The experience is clunky, inefficient, and fraught with risk. This is where our third revolutionary tool promises to shatter the old paradigm entirely: quantum communication networks. This technology sounds like it's pulled from the pages of a physics textbook, and in a way it is, but its practical application is closer than you might think. At its heart is one of the most bizarre and fascinating phenomena in the universe: quantum entanglement. Imagine two particles, perhaps photons of light, that are created together or interact in a specific way. They become inextricably linked or entangled. Now, separate them by any distance across a room, across a continent, or across the solar system. What happens to one particle will instantly affect the other, no matter how far apart they are. It's as if you had two magical dice that, no matter where they were, always landed on the same number at the exact same moment. Einstein famously called this spooky action at a distance, and it forms the bedrock of this new communication method. The implications for space exploration are nothing short of breathtaking. By using pairs of entangled particles, we could create a communication channel that allows for the instantaneous transfer of information. An astronaut standing on the surface of Pluto could have a live, uninterrupted video call with mission control on Earth with zero delay. A scientist could pilot a drone through the methane rivers of Titan with the same real-time responsiveness as flying a drone in their own backyard. This instant connection would transform the nature of exploration, merging human intuition and decision-making with robotic presence in a way that is currently impossible. It would erase the feeling of profound isolation that comes with deep space travel, creating a continuous, real-time link between explorers and the planet they left behind. Beyond mere speed, quantum communication offers another colossal advantage: absolute, unbreakable security. In a quantum network, any attempt to eavesdrop on or intercept the signal would immediately disrupt the delicate entangled state of the particles. This disruption would be instantly detectable to both the sender and the receiver, alerting them to the intrusion and rendering the stolen information useless. For missions that may one day involve sensitive scientific discoveries or even geopolitical considerations, this level of security is paramount. It ensures that commands cannot be hijacked and that precious data streams from distant worlds remain pristine and confidential. This technology wouldn't just make our communications faster, it would make them impervious to interference, creating a trusted and secure nervous system for all our activities across the solar system. Envision a future where this isn't just a point-to-point link but a fully integrated web. A constellation of satellites in orbit around Mars, each equipped with quantum transceivers, could form a local internet, a planetary network that any rover, lander, or future astronaut could tap into with lightning speed and perfect clarity. Data from a rover exploring a canyon could be instantly shared with a habitat base dozens of miles away, or with an orbiter overhead that then relays it directly to Earth. This seamless, instantaneous flow of information would turn individual missions into a unified, coordinated effort, a true network of exploration where every asset is aware of every other, working in perfect real-time harmony. Quantum communication is the key that will unlock this future, finally cutting the cord that has limited our reach and our understanding for so long. Now, while quantum networks handle the flow of information, we need the right tools to generate that priceless data in the first place. To truly understand an alien world, you need to do more than just look at it. You need to know what it's fundamentally made of, atom by atom. This is the domain of our fourth revolutionary tool, advanced spectrometers for elemental analysis. Think of these devices as the ultimate chemical detectives. Where our eyes see just a gray rock or a patch of red sand, a spectrometer sees a complex story written in the language of elements and molecules, revealing a history of volcanic activity, ancient water flows, or even the faint chemical whispers of past life. The principle behind these instruments is as elegant as it is powerful. Every element and compound in the universe absorbs and emits light at unique, signature wavelengths, its own chemical barcode. A spectrometer works by shining a specific type of energy, like a laser or a beam of X-rays, onto a sample and then meticulously analyzing the light that bounces back or is given off. It's not unlike how a prism splits white light into a rainbow, but a spectrometer does this with incredible precision, measuring the exact colors of light to identify the specific ingredients present. The most advanced versions, like the ones on the Perseverance rover, can fire a laser powerful enough to vaporize a tiny pinprick of rock from over 20 feet away, creating a small puff of plasma whose light signature is then read to determine the rock's composition. This means scientists can analyze a dangerous cliff face or a precarious sand dune without ever needing to risk the rover getting close. The real magic, however, lies in what these readings can tell us. It's one thing to know a rock contains iron and silicon. It's another thing entirely to detect the specific clay minerals that only form in the presence of neutral, life-friendly water, or to spot the complex organic compounds that are the building blocks of life as we know it. These are the clues that transform a geological survey into a genuine hunt for habitable environments and ultimately for biosignatures. A spectrometer's data is what allows a mission scientist to point at a readout and say, "See that spike? That's a phosphate, and that pattern suggests this rock formed in a long-vanished lake. That's where we need to drill." It turns a vast, unknown landscape into a series of promising targets, separating mundane dirt from potentially groundbreaking discovery. And the evolution of this tool is a story of brilliant miniaturization. The spectrometers of decades past were room-sized behemoths confined to Earth-bound laboratories. Today, they are marvels of engineering, shrunk down to the size of a soup can or even a deck of cards, yet possessing power and sensitivity that would have been unimaginable to earlier generations. This miniaturization is what allows them to be mounted on the arms of rovers, integrated into the bodies of flying drones, or even held in the hand of an astronaut. This portability means the analysis happens right there on the spot. There's no need to play the agonizing waiting game of collecting a sample, storing it, and then years later launching it back to Earth for study. The laboratory comes to the sample, providing real-time answers that immediately shape the course of the mission. A drone flying over a Martian canyon can use its onboard spectrometer to map the chemical composition of the cliff walls below it, identifying mineral streaks indicative of past groundwater flow, and then radio the coordinates of the most interesting spot to a rover waiting below, directing it to drive over for a closer look. This isn't just science, it's a dynamic, responsive conversation with another world, and it's all made possible by this unparalleled window into the elemental soul of alien terrain. Now, imagine a material that possesses a kind of built-in immune system, a capability to sense injury and respond by healing itself. This isn't fantasy. It's the reality of self-healing materials, and for the brutal environment of space, this technology is nothing short of a lifesaver. The vacuum of space is a relentless and unforgiving place. It subjects everything to a constant barrage of threats: tiny micrometeorites traveling faster than bullets, extreme temperature swings that can shatter metal, and intense radiation that slowly breaks down molecular bonds. A single pinprick-sized puncture in a spacesuit or a hairline crack in a habitat wall isn't just a maintenance issue, it's a potential death sentence. Traditionally, this meant designing everything with massive safety margins, bulky redundancy, and complex repair protocols that often required astronauts to perform dangerous extravehicular activities. Self-healing materials fundamentally change this equation, moving us from a philosophy of passive durability to active resilience. The brilliance of these materials lies in their biomimicry. They take a page from nature's playbook. Consider how your skin heals a small cut, blood clots, scabs form, and new tissue grows to seal the wound. Engineers have created synthetic versions of this process. One of the most common methods involves embedding a material with millions of microscopic capsules like tiny bubbles, filled with a liquid healing agent. When a crack forms in the material, it propagates through it, rupturing these capsules in its path. The healing agent is released, flows into the crack, and comes into contact with a catalyst that is also embedded within the material. This triggers a chemical reaction, causing the liquid to harden into a solid polymer that glues the crack back together, effectively healing the wound. It's a completely automated process requiring no external trigger, no human intervention, and it can work again and again in the same spot as long as there are fresh capsules to rupture. Another fascinating approach uses shape memory polymers. These are smart materials that can be programmed to remember a specific shape. If this material is dented, cracked, or bent out of form, applying a specific stimulus like a slight increase in heat causes it to snap back to its original, undamaged configuration. You could almost think of it as a material with muscle memory. On the Moon, where daytime temperatures can soar well past the boiling point of water, the sun's heat alone might be enough to trigger this healing response. For other environments, a small electrical current could be applied to warm the material and activate its memory. This method is particularly powerful for repairing larger-scale deformations that might occur from a minor impact or structural stress. The applications for this technology are as vast as they are critical. Picture an astronaut spacesuit, the most personal and vital piece of equipment. A tiny micrometeoroid strike could, in an instant, compromise its integrity. With a layer of self-healing material, the suit could seal that puncture within seconds, preventing any loss of precious air and maintaining a safe pressure for the explorer inside. On a larger scale, the inflatable modules of a Mars habitat, often vulnerable to abrasion from dust storms or radiation degradation, could have walls lined with these materials. A scratch from a blowing piece of Martian grit wouldn't be a cause for alarm. It would be a temporary flaw the habitat itself would simply fix. Even the internal systems benefit. Wiring insulation that self-heals could prevent dangerous short circuits. Sealants around airlocks that automatically maintain their integrity would ensure no air leaks out over time. This transforms every piece of hardware from a static, decaying object into a dynamic, self-sustaining system. This shift towards autonomy and resilience is perhaps the most profound aspect of self-healing materials. It drastically reduces the maintenance burden on human crews, freeing them from constant, tedious repair work and allowing them to focus on the real mission, exploration and science. More importantly, it injects a powerful layer of safety and reliability into every aspect of a mission. As we plan for longer journeys to more distant and hostile worlds, places where a resupply mission or an emergency return is impossible, having equipment and structures that can maintain themselves is not just a nice advantage, it is an absolute necessity for survival. This technology gives our future outposts a fighting chance, allowing them to endure and thrive in environments that would otherwise consume them. But to reach those pristine samples, we need to get through the tough outer shell, and that's exactly where our sixth revolutionary tool comes into play: plasma drills for subsurface exploration. For centuries, geologists have understood that the real story is often buried, hidden beneath the surface away from the weathering effects of wind and radiation. On Earth, we use powerful mechanical drills to bore into rock and ice, but these traditional methods face immense challenges in space. The frigid cold can make metal brittle, dust can jam moving parts, and the sheer power required to grind through meters of rock is a huge drain on a mission's limited energy budget. A mechanical drill bit is also subject to incredible wear and tear, risking a mission-critical failure millions of miles from the nearest machine shop. Plasma drilling offers a brilliant and elegant solution to all of these problems, trading brute mechanical force for the sheer, unadulterated power of concentrated energy. The principle is as straightforward as it is devastatingly effective. Instead of a spinning, grinding bit, a plasma drill features a nozzle that emits a jet of superheated, ionized gas plasma. This isn't just hot air, we're talking about temperatures that can rival the surface of the sun, focused into a needle-thin beam. When this beam hits a surface, whether it's water ice as hard as granite on Europa or volcanic basalt on Mars, it doesn't grind or crush. It instantly vaporizes the material directly in its path. The resulting gases are then suctioned away, leaving behind a perfectly smooth, glass-lined borehole. It's a fundamentally different approach. Rather than mechanically breaking rock, it simply disintegrates it atom by atom, clearing a path with minimal physical contact. This means there are almost no moving parts to seize up in the cold, no bits to become dulled or stuck, and the process is incredibly energy efficient compared to the constant torque required to turn a mechanical drill against immense pressure. This capability opens up entirely new frontiers for exploration, most notably the search for life beyond Earth. One of the most exciting targets in our solar system is Europa, Jupiter's ice-covered moon. Scientists are almost certain that a vast, global saltwater ocean sloshes beneath its frozen crust, an ocean that could contain more liquid water than all of Earth's combined. This deep, dark water, warmed by the gravitational tugging of Jupiter, is considered one of the most promising places to look for extraterrestrial life. But how do you get to it? The ice shell is estimated to be kilometers thick. A mechanical drill would be a hopeless endeavor, but a plasma probe, often called a cryobot, could slowly and steadily melt its way down, descending through the ice like a hot knife through butter. As it goes, it could pause to analyze the layers it passes through, each layer a frozen page in the moon's history, until it finally breaches the ceiling of the ocean itself, releasing a small, autonomous submarine to explore the alien sea. The applications extend far beyond icy moons. On Mars, the surface is a hostile place, bombarded by radiation that would have sterilized any evidence of past life billions of years ago. But just a few meters underground, that radiation signature drops off dramatically. If life ever did get a foothold on the red planet, its molecular fossils are likely buried in those protected subsurface layers. A plasma drill mounted on a rover could provide access to this pristine geological record, vaporizing thin slices of soil and analyzing the resulting gases with onboard mass spectrometers. It could detect the subtle chemical fingerprints of ancient organic compounds, the telltale signs of long-dead microbial communities, without ever needing to bring a physically complex sample collection system into the equation. The analysis happens in real time as the drilling occurs, turning the drill itself into a sophisticated scientific instrument. Perhaps most impressively, these systems are designed to be their own geologists. Integrated sensors can perform immediate spectroscopic analysis on the vaporized material, giving instant feedback on the composition of what's being drilled through. Is this layer primarily water ice with ammonia inclusions? Is that stratum rich in clay minerals that only form in water? The drill can adjust its power and pace based on what it finds, and it can even be programmed to automatically steer towards layers of higher scientific interest, following a promising seam of minerals like a high-tech bloodhound on the trail. This transforms the act of drilling from a simple, dumb process of making a hole into an intelligent, investigative dialogue with the subsurface, allowing us to not just access the secrets hidden below, but to understand their context and their story as we uncover them. Now, let's shift our perspective from the tools that analyze and manipulate the environment to the ones that help us understand our place within it. Navigating an alien world is a profoundly disorienting experience. There are no road signs, no GPS satellites overhead, and the terrain itself is a constantly shifting puzzle of hidden dangers. An astronaut on Mars might look out and see a vast, rolling plain that seems perfectly safe, but what their eyes can't perceive is the layer of treacherous, sinkhole-prone dust just beneath the surface, or the fact that the most scientifically interesting rock formation is actually just behind a ridge, completely out of view. Relying on a flat, two-dimensional map on a tablet screen is a clumsy and inadequate solution. It forces the explorer to constantly look down and away from their surroundings, breaking their focus and pulling them out of the moment. This is where our seventh revolutionary tool transforms the entire experience: holographic navigation interfaces. Imagine instead of looking down at a screen, the explorer simply glances through their helmet visor. With a simple voice command or a tap on their wrist-mounted control, the entire landscape in front of them suddenly comes alive with information. A three-dimensional, semi-transparent map blooms into existence, perfectly overlaying and aligning with the real world. This isn't a generic map, it's a dynamic, real-time data visualization. The safe path they should walk is highlighted in a soft, pulsing blue line snaking across the ground. A nearby crater, its edge obscured in shadow, is outlined in a cautionary amber glow, with a small data tag floating beside it indicating its depth and the stability of its rim. In the distance, a previously identified mineral deposit shimmers with a green marker, and a tiny, virtual flag planted by a teammate days ago denotes a site that requires further sampling. The explorer can reach out with a gloved hand and literally grab this holographic projection, rotating the entire landscape to view it from a different angle, or pinching their fingers to zoom in on a specific feature for a closer look. It's the difference between trying to find a friend in a crowded city using a static paper map versus having a magical floating arrow that points directly to them, constantly updating with every step you take. This technology is powered by a fusion of incredible hardware and sophisticated software. The helmet visor itself is a marvel, embedding micro-projectors that can cast light directly onto the retina, creating the illusion of solid objects floating in space. Outside, a network of sensors including LiDAR, radar, and high-resolution cameras mounted on the astronaut's suit, their rover, or even orbiting satellites constantly scans the environment. This torrent of spatial data is processed by onboard artificial intelligence, which stitches it all together into a precise, three-dimensional model of the world. The AI is the true genius behind the scenes. It doesn't just display raw data, it interprets it. It can analyze the texture of the soil from camera feeds to predict its load-bearing capacity and flag a patch of loose sand as a potential hazard. It can correlate current weather data with topographic maps to warn of an approaching dust storm and plot the fastest route to shelter. It can even integrate data from other tools like the spectrometers we discussed earlier, so that a rock rich in organic molecules doesn't just look like any other rock. It glows with a unique signature, instantly drawing the explorer's eye to the most promising scientific targets. The benefits for both human and robotic explorers are profound, touching on both safety and scientific efficiency. For an astronaut, this system dramatically reduces cognitive load. They are no longer burdened with the mentally exhausting task of constantly translating a two-dimensional map into a three-dimensional world while simultaneously watching their step, monitoring their oxygen levels, and conducting experiments. The holographic interface presents the information they need, exactly when and where they need it, allowing them to maintain full situational awareness. In a low-visibility scenario, like the pitch-black darkness of a lunar crater permanently shadowed from the sun or the orange haze of a global Martian dust storm, this tool becomes indispensable. It can use subsurface radar data to project a view of the hidden terrain beneath the obscuring layer, effectively allowing the explorer to see through the storm or the darkness, navigating with a confidence that would otherwise be impossible. For a remote operator on Earth guiding a rover millions of miles away, this same technology provides an immersive, God's-eye view of the operation, making complex maneuvers like precision drilling or sample collection feel as intuitive as playing a highly realistic video game, but with consequences that are very, very real. This approach to robotics, often called biomimicry, starts with a simple but profound realization. Evolution is the most brilliant and relentless engineer in history. Over countless millennia, nature has conducted a brutal, planet-wide research and development program, testing endless designs and keeping only the most successful, efficient, and resilient solutions. The creatures that thrive in Earth's most extreme environments, the crushing depths of the ocean, the shifting sands of deserts, the frozen polar wastes have already solved many of the same problems we face on other worlds. Instead of trying to reinvent the wheel, scientists and engineers are now looking to these masterpieces of natural selection for inspiration, reverse engineering their brilliant strategies for our own purposes in space. Consider the incredible challenge of exploring the labyrinthine lava tubes that snake beneath the surface of the Moon or Mars. These caves are tantalizing targets. Their protected interiors could shield astronauts from radiation and meteoroid impacts, making them ideal locations for future habitats. They might even preserve evidence of past life or water ice. But sending a traditional wheeled rover into such a place is a recipe for disaster. The terrain is a jumbled chaos of boulders, steep inclines, and precarious ledges. A wheel or a track gets stuck all too easily. The solution, a robot that moves like a snake. These serpentine explorers are long, slender, and modular, composed of multiple segments that can twist and bend independently. They don't roll, they slither, sidewind, or concertina their way across impossible ground. They can anchor one part of their body to a stable rock and then reach forward with the rest, probing deep into crevices no human or conventional robot could ever access. Some designs even incorporate a periscope-like camera on the head, allowing them to peek over obstacles or down into pits, transmitting a live feed back to the operator and acting as truly fearless scouts. Then there's the challenge of atmosphere or the lack thereof. The thin air on Mars, with just 1% of the pressure of Earth's atmosphere, renders conventional aircraft nearly useless. The blades of a standard drone or helicopter have almost nothing to push against to generate lift. But NASA's Ingenuity helicopter proved it was possible with incredibly fast-spinning, lightweight rotors. The next step in this aerial evolution takes its cues from nature's flyers. Imagine a drone with wings that flap like a bird or an insect. This method of flight, known as biomimetic propulsion, can be far more efficient and stable in a low-density atmosphere. The complex motion of a flapping wing can generate vortices that create powerful lift with less energy than a spinning rotor. These birdbots could be incredibly agile, capable of taking off and landing vertically, hovering in place to investigate a specific spot, or soaring on thermal currents to cover vast distances and map territory from above. On a world like Saturn's moon Titan, which has a thick atmosphere and low gravity, such flying machines could become the primary explorers, soaring over its methane lakes and organic sand dunes for years. The mimicry goes beyond mere shape and movement. It extends into the very philosophy of how these robots behave. This is where the concept of swarm intelligence comes into play, mirroring the collective behavior of insects like ants or bees. Instead of one large, expensive, and vulnerable robot, a mission might deploy dozens of small, simple, and inexpensive bio-inspired units. Individually, each unit has limited capabilities, but as a collective, they exhibit a powerful emergent intelligence. They could spread out to survey a large area quickly, communicating with each other to mark interesting finds and call over companions for a closer look. If one unit becomes damaged or stuck, the others can work around it, and the loss of a single member doesn't doom the entire mission. This creates a robust and resilient system, much like an ant colony that continues to function even if many individual ants are lost. They are disposable pioneers designed to take risks that would be unthinkable for a multi-billion-dollar flagship rover, venturing into the most dangerous and promising places to ensure that the science gets done. For decades, the fundamental equation of space exploration has been brutally simple, and it has held us back more than any technological barrier. The equation is this: everything you need to survive and work must be brought with you from Earth. Every liter of water, every breath of oxygen, every kilogram of building material, every watt of power from a finite fuel cell. It all has to be launched on a rocket at a cost of tens of thousands of dollars per kilogram. This isn't just expensive, it's profoundly limiting. It dictates mission duration, crew size, and ambition, creating a fragile chain of dependency that stretches back to our home planet. It means that any long-term presence on another world is perpetually one failed resupply mission away from catastrophe. But what if we could break that chain? What if, instead of painstakingly carrying every single resource with us, we learn to live off the land? This is the powerful promise of our ninth revolutionary tool, in-situ resource utilization, or ISRU. In essence, it's the art and science of turning the stuff of other worlds into the stuff of life and exploration. The concept is a paradigm shift in how we approach space travel. Rather than seeing an alien environment as a hostile wasteland to be endured, ISRU allows us to see it as a landscape rich with potential raw materials. It's about looking at the rusty red soil of Mars not just as dust, but as a source of iron, silicon, and oxygen. It's about gazing at the permanently shadowed craters of the Moon not as frozen voids, but as reservoirs of pristine water ice. The tools for this transformation are already moving from the drawing board into prototype testing. One of the most critical and immediate applications is the production of breathable air. The Martian atmosphere, while incredibly thin, is 96% carbon dioxide. A device known as MOXIE, which flew aboard the Perseverance rover, has already proven this concept spectacularly. It's essentially an electronic tree that sucks in the thin Martian air, electrochemically splits the carbon dioxide molecules, and isolates pure, breathable oxygen. On a larger scale, such a device could continuously fill the tanks of a habitat, ensuring a limitless supply of air for astronauts indefinitely, completely eliminating the need to ship it from Earth. But oxygen is just the beginning. Water is the true lifeblood of a mission, needed for drinking, growing food, and even as a component for rocket fuel. ISRU systems are designed to mine this water directly from the ground. On the Moon, prospector missions will likely use rovers equipped with drill rigs and heating elements to excavate soil from the shadowed polar regions and then slowly bake it in an oven, capturing the water vapor that sublimates from the ice within. This water can then be purified and stored. On Mars, the process might involve drilling deeper to access subsurface ice deposits, or even extracting the small amounts of water vapor held in the atmosphere. Once you have a reliable source of water, you unlock even more possibilities. Using electrolysis, you can split that water into its component parts, hydrogen and oxygen. The oxygen adds to the breathable air supply, and both gases can be chilled into liquid form to become the propellant for rockets. This is the holy grail of ISRU, creating fuel for the return trip home. Imagine a mission to Mars where the spacecraft arrives with nearly empty fuel tanks because it knows it can manufacture all the propellant it needs for the journey back from the resources available on the planet's surface. This single application slashes the mission's initial launch mass from Earth by more than half, completely rewriting the economics of deep space travel. The vision extends beyond mere life support and fuel. ISRU is also the key to building a permanent home. The idea of shipping bags of concrete and stacks of lumber to another planet is laughably impractical. Instead, we will literally build our shelters from the ground up. Regolith, the fine, dusty soil that covers the Moon and Mars, becomes our construction material. We've already discussed 3D printers that use this regolith as ink, but that's just one method. Some concepts involve using simple solar ovens or microwaves to sinter the regolith into solid, ceramic-like bricks. Others propose binding the soil with polymers or even using the sulfur naturally present on the Moon as a binding agent to create a kind of lunar concrete. These techniques allow for the construction of radiation-shielded habitats, garages for rovers, landing pads to prevent rocket exhaust from kicking up damaging dust clouds, and roadways. This approach transforms the entire mission architecture. The first astronauts to arrive might not find a pre-built base waiting for them. Instead, they might land next to a large, automated factory that has been operating for months, using locally sourced materials to print and assemble the habitat, the power systems, and the greenhouses that will become their new home. They arrive not as mere visitors, but as tenants moving into a house built from the very land it stands on. This is the ultimate expression of ISRU. It doesn't just support a mission, it enables a settlement. It is the foundational technology that will allow humanity to transition from being explorers of other worlds to becoming inhabitants of them, truly beginning our journey as a multi-planetary species. Now, let's turn our focus to the human explorers themselves, because all the brilliant robots and intelligent systems in the world cannot replace the ingenuity, intuition, and adaptability of a person on the ground. However, the human body is not naturally built for the extreme demands of alien terrain. The very act of exploring another world is a physically grueling endeavor. On the Moon with its 1/6 Earth gravity, or on Mars with its 1/3, every movement becomes a strange, slow-motion ballet that is deceptively exhausting. The bulky, pressurized spacesuit itself is a challenge to operate in, its stiff joints and internal pressure requiring constant muscular effort just to bend an arm or take a step. An astronaut might feel like they're fighting their own clothing all day, leading to rapid fatigue that drastically shortens the time available for productive work outside the habitat. This is a critical bottleneck. Every minute of extravehicular activity is incredibly precious and must be maximized. The solution to this very human problem is our 10th revolutionary tool, wearable exoskeletons for astronauts. Think of these not as robotic replacements, but as a second, powerful layer of muscle that integrates seamlessly with the astronaut's own body. An exoskeleton is a framework, often made of lightweight composites or advanced alloys, that is worn over the spacesuit. It's equipped with a network of tiny electric motors, actuators, and sensors at the key joints, the hips, knees, ankles, shoulders, and elbows. These components don't move on their own. Instead, they sense the astronaut's intention to move and then provide a powered boost to that motion. When an astronaut goes to lift a heavy rock sample, the exoskeleton's sensors detect the muscle activation and strain, and the motors at the elbow and shoulder instantly kick in, taking 90% of the load. To the astronaut, it feels as if the 40-kilogram rock suddenly weighs only 4 kilograms. This amplification of strength is transformative. It allows a single explorer to move heavy scientific equipment, rearrange large pieces of habitat infrastructure, or conduct lengthy drilling operations without succumbing to muscle fatigue. They can work longer, accomplish more, and end the day feeling energized rather than completely drained. Beyond raw power, these systems provide crucial support and stability. Low-gravity environments play tricks on the human sense of balance and proprioception, the body's awareness of its own position. This can make delicate tasks, like using a fine tool to extract a core sample or setting up a sensitive seismic sensor, surprisingly difficult. An exoskeleton can act as a steadying platform, its legs firmly planted on the ground, providing a stable base that allows the astronaut's arms and hands to perform tasks with the precision of a surgeon. Some designs even include locking mechanisms, allowing the wearer to essentially become a living tripod, holding a perfectly still position for minutes or hours to observe an experiment or wait for the perfect photographic opportunity. This combination of superhuman strength and micrometric precision makes the astronaut a far more capable field scientist. Perhaps the most life-saving aspect of this technology, however, is its role as a continuous health monitor. The exoskeleton's intimate contact with the body allows it to do much more than just assist movement. It can be woven with biometric sensors that track heart rate, respiration, body temperature, and even hydration levels in real time. This data is streamed back to the habitat's medical computer and to mission control on Earth. If the system detects the early signs of overheating or physical distress, it can take autonomous action to protect the astronaut. It could automatically circulate coolants through channels in the suit, suggest a brake by making movements slightly more resistant, or even administer a pre-programmed dose of medication or electrolytes through an integrated port. In a worst-case scenario, if an astronaut were injured and incapacitated, the exoskeleton could potentially enter a rescue mode, using its own power to walk or carry the wearer back to the safety of the airlock, essentially becoming a robotic first responder that brings its patient home. This synergy between human and machine is the true power of the exoskeleton. It doesn't seek to replace the astronaut but to elevate them, to erase their physical limitations and protect their well-being. It ensures that when we send humans to the most challenging and distant worlds, they arrive not as fragile visitors but as empowered, resilient, and supremely capable explorers. They become partners with their robotic counterparts, each excelling in their own roles, with the human mind guiding the mission and the exoskeleton providing the physical prowess to make it happen. While robotic explorers on other worlds are incredible field geologists, there's a fundamental limit to what they can discover on their own, no matter how advanced their onboard laboratories become. The most sophisticated rover is still constrained by the size, weight, and power limitations of its instruments. It can tell us a great deal, but to answer the most profound questions, like whether life ever began on Mars, we need the full firepower of Earth's scientific establishment. We need to place a piece of another world under electron microscopes that can see individual atoms, in mass spectrometers that can detect the faintest trace of complex organic molecules, and in the hands of thousands of brilliant researchers who can bring their own unique expertise and new technologies to bear on the sample for decades to come. This is the monumental challenge and the extraordinary promise of autonomous sample return missions, a logistical ballet of epic proportions performed entirely by robots across millions of miles of interplanetary space. The process begins not with a single spacecraft, but with a carefully orchestrated campaign. The first act is the work of a rover like NASA Perseverance, which is currently acting as an intelligent prospector on Mars. It doesn't just drive around picking up pretty rocks. It's using its suite of tools to identify the most scientifically valuable specimens imaginable. It seeks out rocks that formed in ancient watery environments, clays that could preserve organic material, and even sediments that might contain subtle biosignatures. Once it finds a candidate, it doesn't simply scoop it up. It uses a sophisticated, drill-equipped robotic arm to extract core samples, slender cylindrical pieces of rock about the size of a piece of classroom chalk. These pristine cores are then meticulously sealed inside incredibly clean, hermetic tubes made of titanium or another inert material, ensuring that nothing from Earth contaminates the sample and that nothing from the Martian environment, including any potential pathogens, escapes. The rover then deposits these sealed tubes in a designated cache site on the surface, a carefully mapped depot where they will wait for the next player in this cosmic relay race. The second act requires a new level of robotic precision. A separate mission, the Fetch rover, lands near the cache site. This robot is a specialist designed for one primary purpose: to navigate to the depot, reliably collect the dozens of sample tubes, and load them into a container. This might sound simple, but it's a breathtakingly complex autonomous operation. The Fetch rover must find each tube, perhaps using visual recognition software to identify them amidst the Martian dirt, and then use a specialized manipulator arm to pick them up and stow them securely in a basketball-sized capsule. This capsule is the heart of the mission, a multi-layered, incredibly robust container designed to survive a violent launch from Mars, the harsh conditions of interplanetary space, and a fiery re-entry into Earth's atmosphere without breaching. Once loaded, the Fetch rover delivers this precious cargo to the waiting Mars Ascent Vehicle, a small, multi-stage rocket that stands ready on the surface. The final act is the most dramatic and the most fraught with peril. The Mars Ascent Vehicle, with the sample capsule nestled in its nose cone, ignites its engines and launches from the surface of Mars, the first human-made object to ever take off from another planet. This is an entirely autonomous launch, with no human guidance possible due to the communication delay. It must fly a perfect trajectory to rendezvous with a third spacecraft, an orbiter that has been patiently circling Mars, waiting for this precise moment. The orbiter must locate the ascending vehicle, track it, and then maneuver to intercept and capture the sample capsule after it's released. Once captured, the orbiter seals the capsule inside an additional, ultra-secure biocontainment vessel, effectively adding one more layer of absolute protection. Then it fires its own engines to break orbit and begin the long cruise back to Earth. Upon approach, it releases the capsule on a trajectory that will see it slam into the upper atmosphere over a designated military test range, where it will be slowed by a parachute and recovered by teams waiting on the ground. The value of this Herculean effort is immeasurable. Bringing these samples home allows for a kind of analysis that is simply impossible remotely. Scientists can use techniques that require massive, room-sized equipment. They can slice the rock into sections thinner than a human hair to study its microstructure. They can dissolve tiny pieces to analyze its isotopic ratios, which can reveal the temperature of the ancient water that formed it or even the exact age of the rock. Most importantly, they can adapt their experiments on the fly. If one test suggests the presence of an interesting organic compound, they can immediately design a new, more precise experiment to confirm it. An iterative process of discovery that a remote rover, with its fixed set of instruments, could never accomplish. This isn't just about getting a souvenir from another world. It's about opening up the entire history of a planet to the brightest minds on our own, giving them the raw materials to write a new chapter in the story of our solar system and our place within it. But even as we master the art of bringing pieces of other worlds back to our labs, we face a growing and equally critical challenge: how to get all the data from those distant missions back to Earth in the first place. For over half a century, our interplanetary communication has relied on the same fundamental technology: radio waves. We blast powerful radio signals from massive antennas on Earth, like those in NASA's Deep Space Network, and listen patiently for the faint, whispering reply from a spacecraft millions of miles away. It's a method that works, but it's painfully slow, like trying to drink from a fire hose through a tiny, narrow straw. A single high-resolution image from a Martian rover can take minutes to receive, and downloading the data from a complex experiment might tie up a precious deep space network antenna for hours. As our instruments become more sophisticated, capturing ultra-high-definition video, massive radar maps, and immense spectral datasets, this radio frequency straw is becoming completely overwhelmed. We are, in a very real sense, generating scientific treasure faster than we can ship it home. This data bottleneck is the problem that our 12th revolutionary tool is designed to smash wide open: laser communication systems. The principle behind this technology is a beautiful exercise in simplicity and power. Instead of using the relatively long wavelengths of radio waves, it uses the incredibly short, tight wavelengths of near-infrared light. Think of the difference between trying to push a vast, diffuse cloud of energy across the solar system versus firing an ultra-focused, perfectly coherent needle of light. This needle, a laser beam, can carry orders of magnitude more information because it oscillates much faster, allowing it to be modulated or have data encoded onto it at a far higher rate. We're not talking about a modest improvement, we're talking about a leap from dial-up internet to gigabit fiber optics, but on an interplanetary scale. Where a state-of-the-art radio system might manage to transmit a few hundred kilobits per second from the distance of Mars, a laser communications demonstrator on the same planet has already achieved speeds exceeding 200 megabits per second. That's the difference between waiting 9 weeks to download a complete map of Mars and receiving it in just 9 days. This isn't just an upgrade, it's a paradigm shift that transforms the very nature of a mission's scientific return. The most immediate and thrilling benefit of this speed is the potential for real-time, high-bandwidth experiences from deep space. Imagine watching a live, ultra-high-definition video stream from the surface of Titan as a drone flies over its methane lakes, with no lag or interruption in the signal beyond the speed of light delay itself. Scientists on Earth could observe geological events like a landslide on Mars or a cryovolcanic eruption on Europa as they happen, reacting in real time to guide observations instead of receiving the data long after the event is over. This capability turns a distant robotic mission from a slow, correspondence-based dialogue into an immersive, immediate experience. It allows the public to truly ride along, sharing in the awe of discovery at the same moment the mission team does, fostering a deeper connection to the exploration happening so far from home. For mission control, it means they can send vastly more complex commands and software updates in a single transmission, making the spacecraft themselves more adaptable and intelligent. Beyond raw speed, laser communications offer two other crucial advantages: a pinpoint precision and enhanced security. Because a laser beam is so exceptionally narrow compared to a radio wave, it requires incredibly accurate pointing. The spacecraft must know its own orientation and the position of its receiving station on Earth with exquisite precision to ensure that its beam, which might be only a few thousand miles wide at Earth's distance, doesn't miss the mark. This sounds like a weakness, but it's actually a tremendous strength. That narrow beam is much harder to intercept or eavesdrop upon, making the communication channel inherently more secure for sensitive mission commands or data. Furthermore, it is far less susceptible to interference from other transmissions or natural sources, resulting in a cleaner, more reliable signal. This precision also means that the ground-based receivers can be much smaller. Instead of needing a 70-meter-wide radio dish, we can use telescopes that are only a few meters in diameter to catch the laser signal, potentially allowing for a more distributed and flexible global network of optical ground stations, including facilities in space. As this laser communications web expands, linking orbiters, landers, and even constellations of small satellites around other worlds, it will form the high-speed backbone of a true interplanetary internet, ensuring that the flood of discovery from the final frontier flows back to Earth faster than we ever dreamed possible. Beneath the frozen, cracked shell of worlds like Jupiter's moon Europa or Saturn's Enceladus lies perhaps the single most compelling mystery in our solar system: vast global oceans of liquid water. These are not mere pockets of ice. We're talking about depths that could dwarf Earth's own seas, hidden away under an icy crust that acts as a protective ceiling. For astrobiologists, these subsurface oceans are the holy grail of exploration. The combination of liquid water, likely heated by the gravitational tug of war between the Moon and its giant planet, and the complex chemistry we've detected on the surface, makes these environments the most promising places we know of to find life beyond Earth. But there's a monumental challenge: How do you explore an ocean that's locked away under a ceiling of ice that might be 10, 20, or even 30 kilometers thick? You can't land a rover and drill. Conventional technology is utterly useless here. This is a problem that demands a completely new kind of explorer, one that doesn't fight the ice but rather becomes one with it. This is the mission of the Cryobot. A cryobot, or thermal drill, is a specialized probe that operates on a beautifully simple principle: melt your way down. Imagine a sleek, cylindrical device, perhaps the size of a person, pointed at one end like a bullet. Its tip isn't sharp for piercing, but rather houses a powerful heating element. As it touches the ice, this heater, sometimes supplemented by a focused laser or even a small radioisotope power source, begins to liquefy the frozen water directly in front of it. The probe, pulled by its own weight, slowly sinks into the melt hole it creates. As it descends, the water it produces flows around the probe and refreezes behind it, effectively sealing the passage shut. This is a critical feature. It ensures that the pristine environment below is not contaminated by anything from the surface, and conversely, it prevents anything from the deep ocean from accidentally reaching the surface, a key planetary protection protocol. The journey downward is a descent into an unknown realm of extreme conditions. The Cryobot must be an engineering marvel, built to withstand incredible pressures that increase with every meter of depth and to operate in perpetual, crushing cold just a few degrees above absolute zero. Its hull is a thick, pressure-resistant sphere protecting its delicate electronic heart. Power is a constant consideration. The probe needs a steady, reliable energy source to maintain its heat for a journey that could take weeks or even months. Some designs envision a power cable, a literal lifeline trailing all the way back to the surface lander, supplying electricity and allowing for high-bandwidth data transmission. Others propose more autonomous designs with onboard nuclear batteries, free to explore but limited to trickling data back through the ice. And how do you communicate through kilometers of solid ice? Radio waves are useless. They're absorbed almost immediately. The ingenious solution is to use sound. The Cryobot would be equipped with an acoustic transmitter, essentially a powerful underwater speaker. It would send coded pulses of sound pings and clicks vibrating through the ocean, and then through the ice itself. These signals would be picked up by a sensitive seismometer or hydrophone deployed on the surface by the lander, which then relays the data to Earth. It's a slow, painstaking way to communicate, sending only the most crucial bits of information, but it creates a vital link between the hidden explorer and the outside world. The true payoff, the moment that makes this entire technological leap worthwhile, comes when the Cryobot finally breaches the ceiling of the ice and emerges into the ocean itself. Its lights, the first ever to pierce this eternal darkness, would illuminate a world completely alien. Sensors would immediately begin drinking in data, measuring salinity, temperature, pH, and searching for the chemical signatures of biological activity. A forward-looking camera would scan the watery void, while perhaps a side-scan sonar would map the topography of the ice ceiling above and the ocean floor below. The ultimate goal would be to find and sample the water itself. The probe might have small inlet ports to suck in water for onboard analysis, looking for amino acids, lipids, or even cellular structures. Some advanced concepts even include the capability to release a tiny, free-swimming autonomous submarine, a nanobot that could venture further out to explore hydrothermal vents on the ocean floor, places that on Earth are teeming with life entirely independent of sunlight. This is more than just a mission. It's a quest to answer one of humanity's oldest questions. The Cryobot is our best and perhaps only way to directly probe these alien oceans, to turn them from a theoretical possibility into a known quantity. It represents a breathtaking fusion of ambition and engineering, a tool designed to go where no machine has gone before and to see what no eye has ever seen. The data it sends back, even if it's just a single, grainy image of something moving in the water, would forever change our understanding of the universe and our place within it. Yet for all our ingenuity in reaching other worlds, we face an invisible enemy far more persistent and deadly than vacuum or cold, a silent storm that permeates the void between planets. Beyond the protective embrace of Earth's magnetic field, space is flooded with radiation, a constant, invisible hail of high-energy particles that can slice through DNA and silently damage the human body. This isn't a temporary threat like a solar flare that you can wait out. It's a permanent, ambient condition of deep space. On a long journey to Mars, an astronaut would be exposed to radiation doses equivalent to getting a full-body CT scan every 5 or 6 days for the entire trip. The cumulative effect of this exposure dramatically increases the lifetime risk of developing cancer, causing cataracts, or suffering damage to the central nervous system and heart. For decades, the only solution was passive shielding, essentially wrapping a spacecraft in a thick, heavy jacket of materials like lead, polyethylene, or water to absorb the radiation. But the weight penalty was staggering, making such a solution impractical for the long-duration missions we now envision. We needed a smarter, more dynamic defense, and that is precisely what adaptive radiation shielding provides, a system that doesn't just absorb the storm, but actively deflects it. The core innovation of this technology is its shift from a static, one-size-fits-all barrier to a dynamic, intelligent system that responds to the threat in real time. Think of it as the difference between wearing a bulky, inflexible suit of armor versus a modern smart fabric that can instantly become rigid only at the precise point of impact. One of the most promising approaches involves what are known as electroactive polymers. These are smart materials whose molecular structure can be altered by applying an electric current. In their normal state, they might be relatively light and porous, but when sensors detect a surge in radiation like an incoming wave of solar energetic particles from a flare, a current is applied, causing the material's molecules to align and pack together tightly, dramatically increasing its density and therefore its ability to block radiation at the very moment it's needed most. Once the threat passes, the current stops and the material returns to its lighter, more flexible state, saving crucial power and mass. This on-demand protection means the spacecraft doesn't have to be built like a flying bank vault for the entire journey, only transforming into one when the environment turns truly hostile. But the most futuristic and potentially powerful concepts take their inspiration from Earth itself, seeking to create an artificial version of our planet's protective magnetosphere. These active shielding systems would generate magnetic fields or contain volumes of charged plasma around a spacecraft to deflect incoming radioactive particles, much like a real force field from science fiction. One design envisions a pair of large, superconducting rings running around the exterior of the crew module. When energized, they would create a powerful, localized magnetic bubble that would bend the paths of charged particles away from the habitat, funneling them harmlessly around the ship without them ever making contact. Another approach proposes generating a shell or bubble of plasma, an ionized gas that could similarly interact with and deflect incoming radiation. While these systems require significant power to operate, the development of compact fusion reactors or highly efficient solar arrays could make them feasible, offering a protective envelope that travels with the crew, turning their ship into a portable safe haven. The true genius of adaptive shielding lies in its layered, integrated approach. A mission might combine all these methods. The hull itself could be lined with those smart, electroactive polymers for a base level of protection. Superconducting coils would generate a constant, low-level magnetic field to handle the everyday background radiation of deep space. Then, an advanced network of sensors, constantly monitoring radiation levels from the sun and galactic cosmic rays, would be tied into the ship's computer. At the first sign of a major solar event, the system would spring into action, ramping up the power to the magnetic coils to strengthen the defensive bubble while simultaneously signaling the smart hull materials to tighten their molecular structure. This creates a multi-layered, responsive defense system that is both highly effective and incredibly mass-efficient. It moves us from a philosophy of hoping to withstand the storm to one of actively weathering it, ensuring that the men and women who venture into the deep black for months or years at a time can do so with the confidence that they are protected by the most advanced shield humanity can devise. For decades, the image of a space mission was singular and monolithic, a flagship billion-dollar spacecraft painstakingly built over years and carrying the hopes of an entire nation. It was a high-stakes, all-or-nothing gamble, but a quiet revolution has been unfolding in orbit, one that challenges this very notion of exploration. It turns out that sometimes the most powerful intelligence doesn't come from a single giant eye in the sky, but from 1,000 tiny ones working together. This is the core idea behind our 15th revolutionary tool, Nanosatellite Constellations. Imagine not one large, complex satellite monitoring Mars, but a vibrant, dynamic network of 50 or 100 small, inexpensive satellites, each no larger than a shoebox, swarming around the planet in a coordinated ballet. These CubeSats, as they're often called, are the democratizing force of the new space age, and they are poised to completely transform our understanding of other worlds by providing a constant, global perspective that was once a distant dream. The true power of this approach lies in the constellation itself. A single traditional orbiter, no matter how sophisticated, is fundamentally limited. It can only be in one place at a time. It might fly over a specific region of Mars once every few hours, capturing a snapshot of a dust storm as it's beginning to form, and then it's gone, racing around the planet and unable to see how that storm evolves and spreads over the next 90 minutes. It's like trying to understand global weather patterns on Earth with only a single weather balloon. A constellation of nanosatellites shatters this limitation. By spreading these tiny observers across different orbital planes, we can ensure that at any given moment, multiple satellites have their eyes on the planet. This creates a seamless, real-time monitoring system. One CubeSat might detect the initial stirrings of a dust devil in a canyon, another could track its growth and movement 10 minutes later, and a third could observe its interaction with the global atmosphere an hour after that. This networked view allows scientists to study dynamic processes, weather patterns, seasonal changes in polar ice, even the daily cycle of water vapor in the atmosphere, as they actually happen, not just as isolated data points. This shift from snapshot to continuous video is revolutionary for both science and safety. For future astronauts on the surface of Mars, a robust satellite constellation would act as their global weather service and GPS network combined. A lander preparing for descent could receive real-time, hyper-local data on wind shear and dust activity at its landing site, data gathered by a CubeSat that passed over the area just minutes before. Once on the surface, an explorer planning a long traverse could check a forecast that is updated not twice a day, but every few minutes, thanks to the constant stream of atmospheric data flowing in from the swarm overhead. If a global dust storm begins to brew on the other side of the planet, the network would detect its genesis immediately, giving the crew days of warning to secure their habitat and power systems instead of the mere hours they might have with a single orbiter. This transforms planetary exploration from a risky venture undertaken in a poor environment into a well-informed operation with a profound understanding of its surroundings. Perhaps the most transformative aspect of this tool is its accessibility. The traditional model of space exploration required the budget and infrastructure of a superpower. Building a large, multi-ton orbiter is an endeavor that can only be undertaken by a handful of agencies worldwide, but a CubeSat can be designed, built, and tested by a university lab, a small startup, or an emerging space nation for a fraction of that cost. This democratization opens the floodgates for innovation and participation. A team of students in Portugal could design an experiment to measure solar-wind interaction with a planet's magnetic field. A company in Singapore could develop a new, miniaturized communication relay. These individual CubeSats could then hitch a ride on a larger mission as secondary payloads, deploying once the primary spacecraft arrives at its destination. Upon arrival, they join the ever-growing swarm, each contributing its unique capability to the collective intelligence. This model fosters a new, collaborative ecosystem in space exploration, where the goal isn't for one nation to plant a flag, but for humanity as a whole to build a nervous system around another world, one tiny, brilliant node at a time. The human body is a masterpiece of evolution, but it evolved for one specific environment, Earth, with its constant pull of 1 g of gravity. Take that force away, and the entire system begins to slowly, inexorably unravel. We've seen it in astronauts who spend months aboard the International Space Station. Without gravity's constant tug, bones, no longer needed to support weight, begin to leach calcium into the bloodstream, leading to osteoporosis like brittleness. Muscles, especially those in the legs and back, atrophy from disuse, wasting away even with a rigorous daily exercise regimen. The heart, a powerful muscle that normally works against gravity to pump blood upward, becomes lazy and deconditioned. Perhaps most disorienting are the fluids in the body. They shift toward the head, causing sinus congestion, a puffy face, and increased pressure on the eyes that can actually change the shape of the eyeball and degrade vision. These aren't temporary inconveniences. They are profound physiological changes that pose a grave threat to any crew embarking on a multi-year mission to Mars or beyond. They could arrive at their destination too weak to stand, with fragile bones prone to fracture, and unable to perform the demanding work of exploration. For decades, we've treated the symptoms with treadmills, resistance machines, and medication, but it's a constant, losing battle against the fundamental absence of a force that defines our biology. The only genuine, long-term solution isn't to fight the body's reaction to weightlessness, but to simply bring the gravity along for the ride. This is where the concept of artificial gravity moves from science fiction trope to engineering necessity. The principle itself is elegantly simple, a concept you've likely experienced yourself on a playground, roundabout, or a carnival ride. It's centrifugal force. When an object is spun in a circle, anything inside it is pushed outward against the walls of the rotating structure. If you spin a bucket of water in a vertical circle fast enough, the water doesn't fall out at the top. It's pressed firmly against the bottom of the bucket. Now scale that idea up. Imagine a spacecraft designed not as a single, rigid tube, but as two main sections connected by a long truss or a tether, with a heavy counterweight on one end. These two sections begin to rotate around a central point, like two balls on a string swung around your head. For the astronauts inside the crew module, this rotation creates a steady, outward push that feels, for all intents and purposes, just like gravity. Their feet are pressed firmly against the floor, which is actually the outer hull of the rotating module. They can walk normally, pour a drink into a cup, and their bodies are constantly exercised by the simple act of moving around, preventing the devastating atrophy that plagues long-duration space station crews. The engineering challenges, however, are as immense as the benefits. It's not just about spinning, it's about spinning correctly. The rate of rotation and the radius of the spin are critically important. Spin a structure too small too quickly, and you introduce a powerful and deeply nauseating effect called Coriolis force. This is the same effect that makes it difficult to walk in a straight line on a fast-spinning merry-go-round. In a spacecraft, it would mean that every time an astronaut turned their head, the fluid in their inner ear would slosh in a disorienting way, likely causing severe motion sickness. The solution is to create a larger radius. A bigger, slower spinning structure creates a more comfortable and Earth-like gravitational environment. This is why many classic designs, like the iconic spinning wheel from 2001, A Space Odyssey, are so large. The good news is that we may not need a full 1G to see tremendous benefits. Studies suggest that even a partial gravity environment, say Mars like 0.38 G or even Moon like 0.16 G, could be enough to prevent the worst of the bone and muscle loss, and it can be achieved with a smaller, more practical spacecraft design. The most exciting developments are in modular and scalable systems. We may not see a giant rotating starship on the first mission to Mars. Instead, the journey might begin with a smaller, connected system. One compelling design involves the transit vehicle itself. After the crew leaves Earth orbit, their habitation module could separate from the spent rocket stage, unreel a long, strong cable between them, and begin a slow spin. This would transform their entire living quarters into a gentle, artificial gravity environment for the months-long cruise. Upon approaching Mars, they would simply reel the module back in, stop the spin, and prepare for landing. On the surface of a low-gravity world, the concept adapts again. A future Martian base might feature a centrifuge module, a dedicated room that spins to provide a daily dose of higher gravity. Astronauts could schedule time in this gravity gym to read, work, or exercise, giving their bodies the essential stimulus they need to stay healthy until they return to the full gravity of Earth. This tool is more than just a piece of hardware. It is the key to preserving the human instrument itself, ensuring that when we finally reach those distant shores, we arrive not as weakened patients, but as strong, capable, and ready explorers. Yet for all the incredible technology we've developed to survive and explore once we arrive at our destination, we are still fundamentally constrained by one immense and frustrating limitation: the sheer, agonizing amount of time it takes to get anywhere. The vast distances of space are not just empty void. They are a prison of time, forcing missions to spend months or even years in transit, exposing crews to dangerous radiation and psychological strain, and limiting how often we can explore. Our primary means of propulsion for over 70 years has been the chemical rocket, a technology of raw, explosive power that is also incredibly inefficient. It's like trying to drive across a continent in a drag racer. You have immense acceleration for a very short time, and then you simply coast for the remaining 99% of the journey, a prisoner of orbital mechanics and inertia. To break free from this celestial crawl, we need a new generation of engines, ones that don't just provide a brief, fiery kick, but can sustain a gentle, continuous push for weeks or months on end. This is the promise of advanced propulsion systems, and they are the keys that will finally unlock the solar system for routine exploration. One of the most promising and near-term technologies is the nuclear thermal rocket. This isn't about explosions, it's about harnessing the immense, steady heat of a controlled nuclear reaction. Imagine a rocket engine where liquid hydrogen is pumped into a core full of uranium fuel elements. The nuclear fission superheats this hydrogen propellant to temperatures far beyond what any chemical combustion could achieve, transforming it into an incredibly energetic plasma that then blasts out of a nozzle, creating thrust. The beauty of this system is its efficiency, measured in what engineers call specific impulse. A nuclear thermal rocket could be roughly twice as efficient as the best chemical engines. This doesn't necessarily mean it would make the ship go twice as fast in a single burst, but rather that it can maintain its thrust for much longer, enabling a much more direct and faster trajectory. A trip to Mars that currently takes 6 to 9 months with chemical propulsion could potentially be slashed to just 3 or 4 months with a nuclear thermal engine. This reduction in transit time is a game changer for crew health, dramatically cutting their exposure to deep space radiation and the debilitating effects of weightlessness. It also makes the entire mission profile less risky, as the crew spends far less time in the vulnerable expanse of interplanetary space. For missions that require even greater efficiency and are willing to trade initial acceleration for incredible long-term speed, there is the elegant concept of the solar sail. This technology does away with the need to carry propellant altogether, instead harnessing the most abundant force in the solar system, the light of the sun. A solar sail is a gigantic, incredibly thin and reflective sheet of material, often mylar, deployed in space. Although photons of light have no mass, they do carry momentum, and as they bounce off the reflective sail, they impart a tiny, continuous push. This pressure is infinitesimally small, far less than the weight of a sheet of paper on your hand here on Earth. But in the frictionless vacuum of space, where there is nothing to slow it down, that tiny push is constant and cumulative. Day after day, week after week, a solar sail spacecraft would accelerate, building up speeds that could eventually dwarf those of conventional rockets. It's the ultimate tortoise technology, a slow and steady push that wins the race to the outer planets. For journeys to the asteroid belt or beyond, solar sails offer a compelling and completely propellant-free solution, though they are less effective further from the sun where light pressure diminishes. Then there are the more experimental, borderline science fiction concepts that push the very boundaries of physics. For years, there was excitement and controversy around the M-drive, a hypothetical engine that claimed to generate thrust without expelling any propellant whatsoever, seemingly violating the conservation of momentum. While most rigorous testing has since debunked its claims, the pursuit of such ideas highlights a deep desire to find a truly revolutionary breakthrough. More credible, though still in early stages, are concepts like ion thrusters and plasma engines, which are already in use on some deep space probes. These engines work by electrically charging a gas like xenon, and then using powerful magnetic fields to accelerate these ions to tremendous speeds out the back of the engine. They provide only a whisper of thrust comparable to the weight of a single sheet of paper, but they can operate continuously for years. A probe equipped with an ion drive might take months to leave Earth orbit, but by the time it reaches the asteroid belt, it will be traveling at a speed a chemical rocket could never achieve. These engines are the workhorses of unmanned, long-duration science missions, and their technology is constantly being refined for greater power. The impact of these new propulsion systems extends far beyond just shortening the commute. Faster travel fundamentally rewrites the entire logistics of space exploration. It enables a rapid response capability. If a rover on Mars discovers a compelling and time-sensitive scientific target, a follow-up mission with specialized equipment could be launched and arrive within weeks, not years. It makes the concept of regular resupply missions to a lunar or Martian base far more practical and economical. Most importantly, it brings the outer solar system within practical reach. A journey to Jupiter's moons, which currently takes 5 to 7 years with gravity assists, could be conceivable in half that time or less with a powerful nuclear thermal or advanced electric propulsion system. These new engines are more than just pieces of hardware. They are the catalysts for a new era of exploration, shrinking the effective size of our solar system and turning what were once grand, once in a generation voyages into routine expeditions. They are the foundation upon which we will build a truly interplanetary future. But all the advanced propulsion in the world is useless if the crew isn't prepared for the moment they step onto that alien soil. How do you train for an environment that is, by its very nature, completely alien? You can't exactly build a full-scale replica of Mars in a warehouse, and the psychological disorientation of a new gravity, a strange sky, and a landscape devoid of any familiar landmarks is impossible to simulate with textbooks or videos. This is where our 18th revolutionary tool creates a bridge between the known and the unknown, building a mental and muscle memory for worlds we've never visited. Virtual reality training simulators are transforming astronaut preparation from an abstract exercise into a deeply visceral and practical experience, effectively allowing explorers to walk on Mars months or even years before they ever leave Earth. The power of these systems lies in their incredible data-driven authenticity. This isn't the blocky, cartoonish VR of early video games. It's a hyper-realistic digital twin built from petabytes of information sent back by our robotic pioneers. Every boulder, every slope, every distant mesa in a Martian training simulation is painstakingly recreated using high-resolution imagery from orbiters like the Mars Reconnaissance Orbiter and detailed terrain maps from rovers like Curiosity and Perseverance. The lighting is calibrated to match the specific, dust-diffused quality of sunlight on Mars. The colors are corrected to reflect the true, rusty hues of the landscape, not the enhanced versions sometimes released for public consumption. When an astronaut in training looks down at their virtual feet, they see the specific texture of the regolith, the way it crunches and shifts, all based on real physics models derived from watching rover wheels interact with the soil. This obsessive attention to detail is what tricks the brain into full immersion, making the experience feel less like a simulation and more like a memory of a place you've actually been. This realism is then harnessed for intensely practical training scenarios that go far beyond simple familiarization. A crew preparing for a mission to the Moon's South Pole can don their VR headsets and find themselves standing on the rim of Shackleton Crater, a place of perpetual shadows and brilliant, contrasting light. Their task might be to navigate to a specific patch of ground suspected of harboring water ice, all while managing their simulated oxygen levels, power consumption, and communication link. Suddenly, a virtual malfunction alert flashes, a drop in suit pressure. The training doesn't pause. The astronaut must now diagnose the problem using their virtual control panel, locate the leak, and practice the exact procedure for applying an emergency sealant patch, all while their heart rate spikes and the immersive pressure of the situation feels utterly real. They can practice setting up a complex solar array, deploying a seismic sensor network, or even conducting a delicate geological sampling procedure, repeating the tasks dozens of times until the movements become second nature. This builds a robust muscle memory and a profound familiarity with their tools and protocols, so when they finally perform these actions for real, millions of miles from home, it feels like just another day at the office. Perhaps the most transformative aspect of this technology is its dynamic and collaborative nature. These simulators are not static experiences. They are living worlds that can be updated overnight. When a new rover on Mars discovers a previously unknown type of treacherous, fluffy dust that behaves like quicksand, that data can be fed into the simulator the next day, and every astronaut in training can immediately experience and learn to recognize that new hazard. Furthermore, these are often multi-user environments. An entire crew, each in their own VR rig located in different parts of the world, can meet up in a shared virtual space on the slopes of Olympus Mons. They can practice their communication protocols, work through complex, coordinated tasks like setting up a habitat, and run through emergency drills where they must work together to save a crewmate in distress. This builds not just individual competence but essential team cohesion and trust, allowing them to develop a seamless rhythm long before they are locked together in a tiny spacecraft. By blending the virtual and the real so effectively, we are not just training astronauts, we are pre-experiencing the mission, working out the kinks, and building the confidence that comes from having already faced the unknown and prevailed, all from the safety of our own planet. While rovers give us an intimate, hands-on perspective of alien worlds, their view is inherently limited to the path directly ahead, like a geologist studying a vast canyon one rock at a time. To truly understand the grand scale and interconnected nature of these landscapes, we need to rise above it all to see the forest for the trees. This is where drone scouts revolutionize the game, transforming our exploration strategy from a ground-level crawl to a comprehensive, three-dimensional understanding. These aren't the simple quadcopters you might fly in a park. They are sophisticated aerial robots, engineered from the ground up to conquer atmospheres thinner than Earth's highest peaks and gravitational pulls weaker than our own. Their primary gift is perspective. A rover might spend an entire week carefully navigating around a treacherous dune field, but a drone can fly over that same area in minutes, mapping every ripple and identifying the safest, most efficient path through. It can spot the subtle, telltale coloration of a mineral streak on a distant cliff face that would be completely invisible from the ground, instantly transforming a random direction into a high-priority scientific target. The engineering behind these machines is a masterpiece of adaptation. Flying in the Martian atmosphere with its mere 1% of Earth's density is like trying to fly a conventional aircraft at an altitude of 100,000 feet. To generate enough lift, these drones need to be incredibly lightweight, with large rotor blades that spin at astonishing speeds, thousands of revolutions per minute. NASA Ingenuity helicopter, the first aircraft to fly on another world, was a stunning proof of concept, a technology demonstrator that showed it was possible. Its successors, however, are being designed as full-fledged scientific partners. They will carry their own suites of miniaturized instruments, high-resolution cameras to create detailed topographic maps, compact spectrometers to analyze the chemical composition of rocks from the air, and even ground-penetrating radar to peer beneath the surface and identify buried ice deposits or geological structures. This turns each flight into a powerful surveying mission, covering in hours what would take a rover months to traverse. The true potential of this technology is unlocked when these drones operate not as solitary scouts, but as coordinated teams. Imagine a mission to a large, complex crater on Mars. A lander touches down and releases a small swarm of 4 or 5 aerial drones. They immediately take flight and disperse, each assigned a different quadrant of the crater to survey. One might map the steep, unstable inner walls, identifying layers of sedimentary rock that hold clues to the planet's wet past. Another could fly over the central peak, using its radar to probe for subsurface water ice. A third might act as a dedicated communications relay, positioning itself high above the crater rim to maintain a strong, uninterrupted data link between the rovers on the ground and the orbiter overhead, ensuring not a single byte of precious data is lost. This collaborative approach creates a rich, real-time tapestry of information, a holistic view of the environment that allows scientists and mission planners to make the most intelligent decisions about where to go and what to study next. This aerial perspective is not just about efficiency, it's about accessing the utterly inaccessible. Consider the destination of a near-Earth asteroid, a tiny world with almost negligible gravity. Landing a traditional rover there is nearly impossible, as it would likely bounce off into space, but a drone or a swarm of them could hop, hover, and gently land across its surface using tiny thrusters to maneuver in the void. They could map the entire asteroid from every angle, collecting samples from its most rugged and scientifically interesting terrain. On a world like Saturn's moon Titan, with its thick atmosphere and low gravity, drone technology becomes the undisputed champion of exploration. A nuclear-powered drone, like the proposed Dragonfly mission, could spend years flying from one site to another across hundreds of miles, sampling the complex organic chemistry of its methane lakes and sand dunes, essentially acting as a flying laboratory in an alien sky. These drones are more than just tools, they are our avatars in the skies of other worlds, granting us the gift of flight and a God's eye view that finally allows us to see these alien landscapes not as foreign wastelands, but as complex, interconnected worlds waiting to be understood. But all these incredible tools for exploration and construction share one fundamental, non-negotiable requirement. They are useless if the astronauts themselves cannot survive. For short missions, we can rely on what's known as an open-loop system. You bring all your oxygen, water, and food with you in tanks and packages, and you simply dump your waste overboard or store it for disposal. It's simple, but it's also incredibly wasteful, heavy, and utterly unsustainable for any mission measured in years, let alone for establishing a permanent presence on another world. The logistics of resupplying a Mars colony from Earth would be astronomically expensive and fraught with risk. The solution is to stop thinking of a spaceship or a habitat as a machine and to start thinking of it as an ecosystem. This is the profound shift behind bio-regenerative life support systems, a technology that moves beyond mere storage and into the realm of creation, turning waste back into wealth and passengers into active participants in a closed, living cycle. At its heart, this concept is a brilliant mimicry of our own planet. Earth doesn't need shipments of air or water from elsewhere. It continuously recycles them through natural processes. A bio-regenerative system aims to recreate these processes on a miniature, managed scale. The most visible and psychologically vital component is the growth of higher plants. Imagine a dedicated module within a Mars habitat, bathed in the efficient glow of LED lights tuned to specific photosynthetic frequencies. Here, rows of carefully selected crops like wheat, potatoes, lettuce, and tomatoes do far more than just provide a fresh, nutritious supplement to packaged food. They are the lungs of the outpost. As they photosynthesize, they absorb the carbon dioxide exhaled by the crew and release fresh, clean oxygen back into the atmosphere. Their transpiration process also releases purified water vapor into the air, which can be condensed and collected, adding to the water supply. This isn't just farming. It's a fundamental atmospheric processing system where dinner is a delicious byproduct of keeping the air breathable. But a sustainable ecosystem must deal with all forms of waste, and this is where the true elegance of the system reveals itself. Human solid waste and inedible plant matter are not trash to be jettisoned. They are valuable nutrients to be recovered. This is where microbial and fungal partners enter the cycle. Specialized bacteria in anaerobic digesters can break down this waste, converting it into a nutrient-rich slurry that can be fed directly back to the plants as fertilizer, completing the nutrient loop. Even more fascinating is the potential role of mycelium, the vast, root-like network of fungi. Mycelium is a master decomposer in nature, and researchers are exploring its ability to not only break down organic waste efficiently, but also to do so in a way that helps purify the resulting water and even strengthen the structural materials of the habitat itself. Some concepts even envision growing these fungal networks into specific shapes to create biodegradable furniture or packaging, a true example of growing what you need on site. The most efficient systems integrate these components into a symbiotic whole, and the best example of this is aquaponics. In an aquaponic loop, you raise fish or other aquatic species in tanks. The waste produced by the fish, which is rich in ammonia, is toxic to them but is manna for plants. This water is circulated to the plant growth beds, where bacteria convert the ammonia into nitrates, a perfect fertilizer. The plants eagerly uptake these nutrients, and in doing so, they filter and clean the water, which is then recirculated back to the fish tanks, crystal clear and ready to be used again. This creates a beautiful, closed-loop symbiosis. The fish feed the plants, and the plants clean the water for the fish. The system produces both plant and animal protein for the crew, all while recycling water and waste with incredible efficiency. It transforms the habitat from a sterile, mechanical environment into a vibrant, living space, a small piece of Earth teeming with life millions of miles from home. The benefits of this approach extend far beyond the sheer physics of survival. The psychological impact of tending to living plants, of seeing green growth, and perhaps even hearing the gentle trickle of water in an aquaponic system cannot be overstated. On a long, isolated mission, this connection to a living garden could be a powerful antidote to confinement and homesickness, a vital reminder of the world they left behind and are working to create anew. This technology represents the ultimate expression of sustainability in space. It's not about packing enough for the trip, it's about creating a system that can sustain the trip indefinitely. By blurring the line between a technological machine and a living ecosystem, bio-regenerative life support doesn't just keep astronauts alive, it allows them to thrive, turning a distant outpost from a desperate foothold into a genuine, self-sustaining home. Yet for all our ability to see landscapes from above and probe them with drills, one of the most vital resources for any future mission remains frustratingly elusive, often hiding just out of sight beneath the surface. Water is the absolute linchpin of sustained exploration. It's not just for drinking. It's a fundamental component for growing food, for manufacturing breathable air, and perhaps most critically, for being split into hydrogen and oxygen to create rocket fuel for the journey home. The problem is, you can't just dig a well anywhere. Blindly excavating vast tracts of alien soil in the hope of striking ice is a hopelessly inefficient and energy-intensive gamble. We needed a way to see through the ground, to map the hidden aquifers and ice deposits with the confidence of a dowser who can actually see the water table. This is the unique and powerful role of the Neutron Spectrometer, a tool that doesn't look at the surface of a world, but rather listens to the whispers coming from deep below. The principle behind this technology is as ingenious as it is indirect, relying on a fundamental interaction between particles. The surface of any planet or moon is constantly being bombarded by cosmic rays, high-energy particles streaming in from deep space. When these cosmic rays slam into the atoms in the soil, they can smash them apart, releasing a shower of secondary particles, including neutrons. Now, here's the key. the behavior of these neutrons changes dramatically depending on what they collide with next. If the soil is made mostly of heavy elements like silicon or iron, the neutrons bouncing through it will retain a lot of their energy. They'll be what scientists call fast or epithermal neutrons. But if those neutrons happen to collide with something very light, like a hydrogen atom, they lose a significant amount of their energy and slow down, becoming thermal neutrons. It's like firing a bullet into a room full of bowling balls versus firing it into a room full of ping-pong balls. In the first case, the bullet ricochets around with most of its speed intact. In the second, it quickly slows down as its energy is absorbed by the lighter objects. A neutron spectrometer is essentially a highly sensitive neutron counter mounted on an orbiter or a rover. It doesn't detect water directly. It measures the energy signature of the neutrons bouncing back up from the subsurface. As it passes over a region, it builds up a map of the neutron flux. A high count of fast, energetic neutrons indicates dry regolith, barren of hydrogen, but a pronounced dip in that count, a deficit of fast neutrons and a corresponding increase in slow thermal neutrons is a telltale signature. It's the instrument's way of shouting, "There's hydrogen down here," and since the most common source of hydrogen in the solar system is water, either as ice or locked away in hydrated minerals, that signal is a virtual guarantee of H2O. The deeper or more concentrated the water deposit, the stronger the neutron shadow it casts, allowing scientists to not just find water, but to estimate its abundance and its depth with remarkable accuracy. This capability has already revolutionized our understanding of our own moon. For centuries, astronomers gazed at the lunar surface and saw a bone-dry, barren world. But data from instruments like the Neutron Spectrometer on NASA's Lunar Prospector mission painted a radically different picture. It revealed that the permanently shadowed craters at the moon's poles, places so cold that sunlight hasn't touched them in billions of years, are actually vast frozen reservoirs. These are not just patches of frost. We're talking about millions of tons of water ice mixed into the soil, a priceless resource waiting for future explorers. This single discovery completely rewrote the playbook for lunar exploration. It meant that a permanent base on the moon could be sustainable, using this local water for life support and fuel, turning the moon from a mere destination into a potential gas station for the rest of the solar system. The same powerful technique is being used right now to guide our exploration of Mars. Orbiting spectrometers have mapped the planet's global hydrogen distribution, identifying regions rich in subsurface ice, particularly in the mid-latitudes. This data is absolutely critical for mission planners. When selecting a landing site for a future human mission, the #1 priority beyond science will be access to water. You would want to land your crew within easy driving distance of a substantial, reliable ice deposit that they can mine. A neutron map provides that crucial intelligence, turning a gamble into a calculated, informed decision. For rovers already on the surface, like Curiosity, smaller neutron spectrometers can perform more localized surveys, helping scientists choose exactly where to drill to have the best chance of hitting hydrated layers. It transforms exploration from a guessing game into a targeted treasure hunt, ensuring that every ounce of effort is spent on the most promising ground. This tool doesn't just find water, it finds possibility, revealing the hidden wet spots on otherwise arid worlds that will ultimately enable humanity to put down roots and stay. Now imagine being able to turn the very atmosphere and soil of an alien world into a living, sensing entity, to create a vast, intelligent skin that feels every change in the environment. This is the extraordinary promise of smart dust sensors, a concept that takes the idea of distributed monitoring to its absolute extreme. The name isn't just a cute metaphor. These are literal motes of technology, each one a self-contained sensor package no larger than a grain of rice or even a speck of sand. The vision is to deploy them not by the handful, but by the thousands or even millions, releasing a cloud of them from an orbiter, a lander, or even a passing rover. Carried by the wind, what little there might be on a world like Mars, they would disperse across a vast area, settling on the ground, lodging in rock crevices, and even coating the stems of alien plants, creating a massive, wireless sensor network that blankets the landscape in an invisible web of data. Each individual mote, despite its microscopic size, is a marvel of micro-electrical mechanical systems, or MEMS technology. It's a complete system on a chip, packing in a power source, likely a tiny solar cell or a beta-voltaic battery that uses the decay of a radioactive isotope for long-term energy, a sensor suite capable of measuring its specific environmental parameters, a rudimentary processor to handle the data, and a micro-radio for communication. They are designed to be incredibly frugal with their energy, spending most of their time in a deep sleep mode, waking up only at scheduled intervals to take a measurement. Perhaps the temperature has dropped 2 degrees, the local pressure is rising, or a specific chemical signature has been detected. They then transmit that tiny packet of data, broadcasting it on a common network frequency to any nearby receiver, be it a passing rover, a stationary lander, or an orbiter overhead. The true power of this system isn't in any single data point from one mote, but in the collective intelligence of the entire swarm. Think of it like the difference between having a single weather station in the middle of a desert versus having 10,000 of them spread across every dune and valley. A traditional lander gives you hyper-accurate data for one single, stationary point. A smart dust network gives you a living, breathing, high-resolution map of an entire region. You could observe how frost forms and sublimates in the early morning across 100 square kilometers, tracking the precise microclimates where it lingers longest. You could monitor the flow of dust devils not as single events, but as vast weather systems, seeing how they form, travel, and dissipate across the terrain. For the first time, we could study the meteorology of another world not from a few isolated points, but with the same dense coverage we expect from weather satellites on Earth. This approach is particularly powerful for monitoring transient and dangerous phenomena. Consider the challenge of studying a geyser on Saturn's moon Enceladus or a cryovulcano on Neptune's moon Triton. Sending a fragile, expensive rover right up to the vent would be far too risky. It could be damaged by the eruption itself or by the unstable ground around it. But you could safely scatter a cloud of smart dust sensors across the area from a distance. Some would be destroyed in the next eruption, but many would survive, providing a front-row seat to the action. They could measure the precise temperature of the ejected material, analyze its chemical composition as it falls back down like snow, and record the seismic vibrations of the event. Because each mote is so inexpensive and disposable, the loss of a few hundred of them is a trivial cost for the priceless data they return from the heart of an alien cataclysm. This allows us to be boldly curious in ways we never could before, venturing into the most dynamic and hazardous places by proxy, using countless tiny, expendable eyes to witness the universe's most powerful forces at work. While the surface of an alien world tells one story through its rocks and canyons, a far older and more fundamental narrative is written in the invisible tapestry of its magnetic field. This force, generated deep within a planet's core, acts as a unique fingerprint, a record of its internal dynamics and its entire geological history. To read this story, we need a tool that can sense the faintest whispers of magnetism, the subtle variations that betray what lies hidden below. This is the precise role of the magnetic anomaly detector, an instrument that doesn't see with light but instead maps the invisible architecture of a world's magnetic soul, turning what was once undetectable into a detailed guide for both science and survival. The principle behind these detectors is beautifully straightforward, even if the data they produce is profoundly complex. At its core, the instrument is a supremely sensitive magnetometer, capable of measuring the strength and direction of a magnetic field with astonishing precision. But it's not interested in the background field itself. It's hunting for the tiny, localized deviations from the norm, the anomalies. As this detector is flown over a landscape on an orbiter or driven across it on a rover, it creates a detailed map of these magnetic highs and lows. A sudden, intense spike in the field strength might indicate a concentrated deposit of highly magnetic iron ore just beneath the surface. A long, linear pattern of alternating high and low readings could trace the outline of an ancient lava flow, where different layers of rock recorded the direction of the planet's magnetic field as they cooled and solidified billions of years ago. It's like using a metal detector that can see through miles of rock, but instead of just finding buried treasure, it's reading the chapters of a planet's autobiography that have been sealed away since its formation. The most profound revelations from this tool come from what is missing as much as from what is present. Earth is shielded by a powerful, global magnetic field generated by the churning of its molten iron core, a planetary dynamo. But Mars presents a fascinating puzzle. Orbiting magnetometers have revealed that the red planet lacks a global magnetic field today, yet they detected incredibly strong, localized magnetic fields frozen into the oldest parts of its crust, particularly in the southern highlands. This was a stunning discovery. It tells us that Mars once did have a global dynamo, a protective magnetic shield just like Earth's, which vanished billions of years ago. As the planet's core cooled and solidified, the dynamo died, and the solar wind began stripping away the atmosphere, ultimately leading to the cold, arid world we see today. Those localized anomalies are the ghostly remnants of that lost shield, a magnetic fossil preserving the moment a world's fate changed forever. By studying their patterns, scientists can even estimate when the dynamo shut down, adding a crucial timestamp to the story of how Mars became uninhabitable. For future human explorers, this data transcends pure science and becomes a practical tool for prospecting and planning. A detailed magnetic map of a region would be an invaluable resource for a crew looking to establish a sustainable base. Those anomalies signaling rich iron or nickel deposits would pinpoint the best locations to mine for raw materials to be used in 3D printers and construction projects, a key part of any in-situ resource utilization strategy. Furthermore, understanding the subsurface geology through its magnetic signature is critical for safety. It could help identify unstable terrain, like areas underlain by weak, sedimentary rocks versus solid, volcanic bedrock, ensuring that habitats and landing pads are built on stable ground. This transforms the magnetic anomaly detector from a passive scientific instrument into an active partner in exploration, providing the actionable intelligence needed to not just understand an alien world, but to successfully build a future upon it. Now imagine a geologist in a lab on Earth, their hands resting on a specialized control console, their eyes covered by a high-resolution virtual reality headset. But through that headset, they aren't looking at a simulation. They are seeing a live, stereoscopic video feed from the surface of Mars. As they move their own head to look left, the camera head on a robot thousands of miles away turns in perfect sync. They reach out with their hand to pick up a rock, and through a sophisticated haptic feedback glove, they feel the precise weight and gritty texture of that Martian stone as the robotic arm lifts it. This is the profound immersion of telepresence robotics, and it shatters the traditional barrier between explorer and exploration. It allows the finest scientific minds on our planet to virtually walk on another world, to lean in for a closer look, and to apply their decades of instinct and training in real time without ever leaving the safety of their home planet. The technology that makes this possible is a symphony of advanced systems working in perfect harmony. The robot itself is a mobile avatar designed for stability and dexterity. It's equipped with multiple high-definition cameras to provide depth perception and a full field of view, often with zoom capabilities that let an operator feel like they're examining a mineral grain under a microscope one moment and surveying a vast canyon the next. High-fidelity microphones capture the faint sounds of the environment, the whisper of an alien wind, the crunch of wheels on regolith, or the whir of its own instruments, adding a crucial layer of auditory immersion that makes the experience feel less remote and more real. But the true magic lies in the haptic feedback systems. These are not simple joysticks. They are force feedback mechanisms that replicate the sensation of touch and resistance. If the robot's arm pushes against a heavy object, the operator feels that push in their own hand. This tactile feedback is essential for performing delicate tasks, like inserting a fragile sample into a container or using a geological hammer without striking too hard and shattering a priceless specimen. It transforms the operator from a distant pilot into a virtual participant, their own muscles and nerves directly connected to the actions of the machine. This capability dramatically expands the human reach into space in two incredibly powerful ways. First, it democratizes expertise. A mission to Mars can only ever support a small, multidisciplinary crew. But with a telepresence robot on the surface, the world's leading expert on Martian mineralogy, a specialist in extremophile biology, or a brilliant structural engineer can all take turns operating the machine, each applying their unique skills to the problem at hand. A puzzling geological formation isn't just described in a report sent back to Earth. The planet's top geologist can virtually step into the scene, kneel down, and examine it with their own experienced eyes, making a definitive diagnosis on the spot. Second, and just as importantly, it acts as a powerful force multiplier for the astronaut crew already on site. The human explorers can focus on the most complex, dangerous, or physically demanding tasks, while the telepresence robots, guided by experts on Earth, handle more routine surveys, preliminary scouting, or long-duration monitoring operations. This collaboration between boots on the ground and minds in the lab creates a continuous, shifting work cycle that operates across multiple time zones and vastly increases the scientific return of the entire mission. The potential of this technology only grows as we look toward the most extreme environments in our solar system. Consider the surface of Venus, a hellscape of crushing pressure and searing heat that would destroy any conventional lander within hours. A telepresence rover, built to withstand those conditions for a longer period, could be controlled by scientists on Earth, allowing them to explore that infernal landscape for days or even weeks. Or imagine the icy shell of Europa. A telepresence robot could be stationed near a crack or a vent, waiting for a plume of water to erupt. When it does, a team of astrobiologists on Earth could immediately take control, guiding the robot's instruments to sample the freshly fallen material in real time, reacting to the dynamic event as if they were truly there. This isn't just about reducing risk, it's about enhancing discovery, putting the right human expertise in the right place at the exact right time, regardless of the millions of miles of empty space in between. It ensures that the intuitive leap, the sudden spark of recognition that so often drives science forward, is not lost to the long delay of a communications lag, but can be acted upon in the moment, bringing the full weight of human curiosity to bear on the greatest mysteries of the cosmos. But while tools like Telepresence robots expand our reach, they all share a single, fundamental requirement: a silent heartbeat that must never stop. Every instrument, every communication, every life support system depends on a constant, unwavering flow of energy. In the unforgiving environment of space, power isn't just a convenience. It is the absolute lifeblood of exploration. And for missions on the surfaces of other worlds, the sun provides the most reliable and sustainable wellspring we could ever hope to find. Solar-generated energy grids are the vital circulatory systems that harness this incredible resource, transforming the faint sunlight of distant planets into the steady electricity that fuels our greatest adventures. The challenge of power generation on another world is vastly different from here on Earth. On Mars, for instance, the sunlight is only about 40% as strong as what we receive on a clear day here, due to the greater distance from the sun. Furthermore, these environments are plagued by immense dust storms that can blot out the sky for weeks, and by long, frigid nights that can last for over 12 hours. Early missions got by with relatively small, rigid panels, but to support a sustained human presence, we need something far more robust and adaptable. This is where advanced photovoltaics come into play. These are not your average rooftop solar panels. They are marvels of materials science, engineered with ultra-efficient cells that can capture a broader spectrum of light, including the weaker, more diffuse sunlight that filters through a dusty Martian atmosphere. Some experimental designs even incorporate multi-junction cells, layers of different materials each tuned to absorb a specific wavelength of light, squeezing every last drop of energy from every photon that strikes them. Of course, capturing energy is only half the battle. Storing it for the long night is the other. This is where the true sophistication of these power grids lies. They are integrated systems, pairing the solar arrays with massive, incredibly durable battery banks or regenerative fuel cells. These aren't like the lithium-ion battery in your phone. They are designed for thousands of charge-discharge cycles and to withstand extreme temperature swings that would destroy lesser components. A regenerative fuel cell is a particularly elegant solution. During the day, excess solar power is used to electrolyze water, splitting it into hydrogen and oxygen gas, which are stored in high-pressure tanks. Then, during the night, these gases are recombined in a fuel cell, generating electricity and producing pure water as a byproduct, a clever closed-loop system that provides both power and a valuable resource for life support. The deployment of these systems is a spectacle of automated engineering in itself. Imagine a lander touching down on the lunar surface. Shortly after landing, a panel on its side opens, and a sophisticated robotic arm unfolds, gently placing a compact package onto the regolith. This package then begins to transform, its sides unfolding like a high-tech origami project, blossoming into a vast, circular array of ultra-thin solar panels that lock into place, angled perfectly toward the sun. This isn't science fiction. Prototypes of these flexible, self-deploying arrays are already being tested. For larger bases, the vision is even more ambitious. Entire fields of panels could be laid out across the landscape, connected by a smart microgrid that dynamically manages power distribution. If one panel becomes covered in dust, the system reroutes power around it. If a habitat's demand spikes because the crew is running a particularly energy-intensive experiment, the grid can prioritize that need, ensuring that critical systems never experience a brownout. This shift to harnessing local energy is perhaps the most crucial step toward true independence from Earth. Relying on shipped nuclear batteries or fuel for generators places a hard limit on mission duration and creates a fragile supply chain stretching across millions of miles. By tapping into the constant, abundant energy of the sun, we sever that tether. A well-designed solar grid paired with sufficient storage can provide all the power needed for habitats, greenhouses, rover charging stations, and even small-scale manufacturing facilities for years on end. It enables missions that are not just longer but bolder, allowing us to power energy-hungry tools like large drills or subsurface radar that were previously unimaginable. This technology transforms a distant outpost from a temporary camp living on borrowed time into a permanent, self-sufficient home, powered by the same star that sustains life on our own world. Just as a doctor uses a stethoscope to listen to a patient's heartbeat and breathing, planetary scientists have their own version of this diagnostic tool to understand the health and history of a world. Seismic sensors, or seismometers, are designed to be exquisitely sensitive ears pressed against the ground of another planet, listening for the faintest vibrations that travel through its interior. These aren't just random rumbles. Every tremor, from the slightest shiver to a full-blown quake, carries a unique signature, a coded message about the materials it passed through and the forces that created it. The fundamental principle is elegant in its simplicity. When an event occurs, a meteorite impact, a landslide, or the tectonic shudder of a Mars quark, it sends out waves of energy that radiate through the planet. Different types of waves travel at different speeds and through different materials. Primary waves, or P waves, are compressional, moving quickly through both solid and liquid material. Secondary waves, or S waves, are slower and can only travel through solids. By precisely timing the arrival of these different waves at a sensor, scientists can perform a kind of cosmic triangulation, not just to locate the source of the quake, but to paint a detailed picture of the planetary interior. It's the difference between seeing a silhouette and getting a full, three-dimensional CT scan. The data from these instruments is what allows us to move from speculation to certainty about what lies beneath the surface. Before we placed seismometers on the moon during the Apollo missions, we could only guess at the structure of its interior. The data those instruments sent back revealed a moon with a layered interior much like Earth's, but one that is largely geologically dead, its core mostly solid and its tectonic activity long since ceased. This told a story of a smaller world that cooled quickly, a crucial chapter in our understanding of how terrestrial planets evolve. More recently, the in-situ lander on Mars carried a supremely sensitive seismometer to the red planet. Its years of listening revealed a planet that is far more seismically active than the Moon, but less so than Earth. By analyzing the paths of hundreds of Mars quarks, scientists were able to make the first direct measurements of the size of Mars's core, the thickness of its crust, and the structure of its mantle. They discovered that the Martian core is larger and less dense than previously thought, likely molten and not generating a protective magnetic field, which helps explain how Mars lost its atmosphere and water over billions of years. This single instrument provided the ground truth that allowed us to calibrate all our previous models, turning abstract theories into concrete facts. The future applications of this technology are perhaps even more thrilling, especially for worlds where the surface is just the beginning of the mystery. Consider an icy moon like Europa. Placing a seismometer on its frozen crust would do more than just measure quakes. It could act as a direct sonar probe into the ocean below. The constant cracking and shifting of the ice shell would generate a cacophony of signals. By listening carefully, scientists could precisely measure the thickness of the ice by timing the echo of waves bouncing off the boundary between ice and liquid water below. They might even detect the sloshing of the ocean itself or the rumble of cryovolcanoes on the seafloor, providing indirect evidence of the hydrothermal vents that could potentially support life. On a small, rubble pile asteroid, a seismometer could reveal how loosely the pieces are held together by gravity, critical information for any future mission that might need to anchor to the surface or attempt to deflect such an object. Every world has its own unique seismic language, a dialect of rumbles and creaks that tells the story of its birth, its evolution, and its current state of being. By learning to listen, we gain the ability to understand not just the skin of these alien terrains, but their very souls. But even as we listen to the grand, planetary-scale stories told by seismic rumblings, some of the most profound discoveries are waiting to be made not in the vastness of a canyon, but in the breathtakingly small world of the atomic scale. Imagine a Rovers spectrometer identifies a curious carbon signature in a Martian rock, a potential hint of past organic activity. It's a thrilling clue, but it's just that, a clue. To move from hint to confirmation, from possibility to proof, we need to see the evidence with our own eyes, not with a microscope, but with a window to the atomic realm. This is the unparalleled power of our 27th revolutionary tool, the atomic force microscope. This instrument doesn't just analyze a sample. It lets us virtually reach out and feel its surface, atom by individual atom, creating a three-dimensional topographical map of the utterly minuscule, transforming a vague chemical signal into a visible, tangible reality. The principle behind this technology is a marvel of precision engineering and subtle physics. At its heart is an incredibly tiny probe, a tip so sharp that its point may be only a single atom wide. This tip is mounted on the end of a flexible, microscopic cantilever, like a minuscule diving board. As the probe is brought excruciatingly close to the surface of a sample, the faint forces that exist at the atomic level, van der Waals forces, electrostatic attractions, cause the cantilever to bend ever so slightly. A laser beam is bounced off the top of the cantilever, and as the cantilever bends, the laser's reflection shifts. A sensitive array of photodiodes detects this minute shift in the laser's position, and a computer uses this information to build a stunningly detailed picture of the surface's peaks and valleys. It's a process of touch, not sight, creating an image by literally feeling the shape of the atomic landscape beneath it. The resolution is so immense that it can distinguish individual atoms and molecules, revealing the very building blocks of a material. This capability is an absolute game changer in the search for extraterrestrial life. Other instruments can tell us that a rock contains carbon, or even specific complex organic molecules. But an atomic force microscope can show us the structure of those molecules. This distinction is everything. Consider the discovery of a potential microfossil. A standard camera might show a tiny, worm-like structure. Is it truly the remnant of an ancient Martian microbe, or is it just an interesting mineral formation that happens to look biological? An atomic force microscope can settle the debate. It could scan the surface of that structure and reveal the detailed cellular wall patterns, the distinct segmentation, or the complex non-crystalline organization that screams biology to a trained scientist. It could even detect the subtle, telltale-handedness or chirality of organic molecules. On Earth, life almost exclusively uses left-handed amino acids and right-handed sugars. Finding that same specific molecular preference in an alien sample would be one of the strongest possible indicators that life, not just random chemistry, was at work. The true genius of this tool for space exploration lies in its remarkable miniaturization. The atomic force microscopes found in university laboratories are often bulky, table-sized instruments that sit on vibration-dampening tables to prevent the slightest tremor from ruining a scan. Engineers have performed miracles in shrinking this technology down to a package small and robust enough to withstand the violence of a rocket launch and the harsh conditions of another world. These space-rated versions are automated marvels. A rover's robotic arm would place a carefully prepared sample onto the microscope stage. The instrument would then take over, autonomously calibrating itself and performing the scan, sending the breathtakingly detailed data back to Earth for scientists to analyze. This brings the full power of a top-tier Earth-based laboratory directly to the field, eliminating the agonizing weight of a sample return mission and allowing for on-the-spot, definitive analysis of the most promising finds. It ensures that a discovery of monumental importance isn't left sitting on a rock on Mars for a decade. It can be identified, confirmed, and celebrated in real time, opening a new window into the microscopic wonders of alien worlds. But to truly power a civilization beyond Earth, to energize the sprawling industrial operations and bustling cities we might one day build under alien skies, we must look beyond even the generous power of the sun and tap into the very engine of the stars themselves. This is the promise of the 28th and final revolutionary tool on our list, a technology that represents the absolute pinnacle of energy generation, fusion power. For all their strengths, solar panels, nuclear batteries, and even fission reactors come with inherent limitations. They are either dependent on sunlight, produce problematic waste, or simply cannot scale to meet the colossal energy demands of a large-scale planetary colony or a high-speed interplanetary transport ship. Fusion power, the process that has lit the universe for billions of years, offers a vision of energy so abundant and so clean that it completely rewrites the rules of what is possible in space exploration. The fundamental principle is breathtaking in its elegance and power, mirroring the reactions that fuel our sun. In a fusion reactor, light atomic nuclei, typically isotopes of hydrogen like deuterium and tritium, are forced together under conditions of immense heat and pressure. When they overcome their natural electromagnetic repulsion and fuse, they form a heavier helium nucleus, and in the process, a tiny amount of mass is converted into a colossal amount of pure energy, as described by Einstein's famous equation. The fuel for this reaction is astonishingly plentiful. Deuterium can be extracted from the water ice we now know is common on the Moon and Mars, and tritium can be bred from lithium, which is also found in lunar and Martian regolith. This means a fusion-powered colony could become completely energy independent, mining its own fuel from the local environment without needing a single shipment from Earth. Furthermore, the waste product is inert helium gas, not the long-lived radioactive isotopes produced by fission, making it an incredibly clean and safe process with minimal environmental impact. The applications for such a power source are as vast as the solar system itself. On the surface of a planet, a single, compact fusion reactor could provide enough electricity to power an entire city-sized habitat, its life support systems, manufacturing facilities, and agricultural domes with energy to spare. It could energize powerful industrial lasers for sintering regolith into construction materials, or running massive water extraction operations that melt entire glaciers. But perhaps the most transformative application is in propulsion. A fusion-powered spacecraft would be a true game-changer. By using magnetic fields to direct the superheated plasma from the fusion reaction out of a nozzle, such an engine could generate a continuous, high-velocity exhaust, enabling speeds that are simply inconceivable with chemical or nuclear thermal rockets. A trip to Mars could be shortened from months to mere weeks, and journeys to the outer planets and their fascinating moons would shift from being multi-decade, generational endeavors to missions measured in just a few years. This wouldn't just be an improvement in propulsion, it would be a fundamental democratization of the solar system, bringing every world within practical reach. While the challenge of achieving sustained, net-positive fusion here on Earth remains one of the great engineering puzzles of our time, the progress is real and accelerating. Breakthroughs in superconducting magnet technology, laser-induced inertial confinement, and advanced plasma physics are bringing the dream closer to reality. For the unique conditions of space, with its natural vacuum and access to copious coolant, the engineering challenges may actually be simpler than on Earth. The development of compact fusion reactors is no longer a fringe idea, but a serious pursuit by both government agencies and private companies. This tool represents the final piece of the energy puzzle, the key that unlocks a future where energy is no longer a constraint on our ambition. It promises a tomorrow where humanity doesn't just visit other worlds, but truly thrives on them, powered by the same cosmic fire that illuminates the heavens. Yet the true magic of this integrated future lies not in the individual technologies, but in the emergent intelligence that arises from their seamless collaboration. Picture a scenario on the distant, icy plains of Europa. A command from Earth sent via a secure quantum link initiates the entire sequence. A lander touches down, and its first act is to deploy a small army of specialized robots. A trio of snake-like, biologically inspired bots immediately slithers into a nearby surface crack, their flexible bodies navigating terrain that would stop a conventional rover cold. As they descend, they use plasma drills to melt through the ice, their path guided by real-time data from a constellation of nanosatellites overhead, which are simultaneously mapping the subsurface structure with penetrating radar. These serpentine pioneers don't work in isolation. They leave behind a trail of smart dust sensors, tiny motes that adhere to the ice walls, creating a wireless network that monitors temperature, pressure, and seismic vibrations, feeding a constant stream of data back to the surface. On the surface, the operation is orchestrated by a central AI housed within the lander. This digital brain processes the flood of information from below and coordinates the surface assets. A swarm of smaller, agile rovers, their bodies made from self-healing materials to withstand the punishing radiation, fan out from the landing site. They are not pre-programmed with a fixed route. Instead, they receive continuous navigation updates from drone scouts flying in the thin atmosphere, their holographic displays projecting safe paths over the treacherous, crevasse-riddled landscape. These rovers are the muscle of the operation, tasked with deploying the heavy infrastructure. Using advanced in-situ resource utilization systems, they process the local water ice, using 3D printers to construct a radiation-shielded dome that will serve as a base of operations, all powered by a compact fusion reactor that provides near-limitless energy. Inside this growing habitat, bio-regenerative life support systems click on, beginning the process of creating a breathable atmosphere and producing food, turning the outpost from a mere station into a living, breathing ecosystem. The human element is woven into this tapestry of technology through telepresence. While the physical dangers are handled by robots, the finest scientific minds on Earth are virtually present. A geologist in Houston wearing a haptic feedback suit can feel the texture of an interesting ice sample collected by a robotic arm, their expertise guiding the next move in real time, thanks to the lag-free quantum connection. An exobiologist in Berlin, analyzing data from an atomic force microscope that's examining a sample at the nanoscale, can request a deeper drill from a cryobot probing the ocean below, all without the decades-long delay a traditional mission would require. This is not a series of disconnected tools. It is a single, distributed organism with sensors for nerves, robots for limbs, and a collective human and artificial intelligence for a brain. Each system covers the weaknesses of another, creating a resilient whole that is far greater than the sum of its parts. The failure of a single rover or the loss of a communication satellite is not a mission-ending catastrophe but a minor hiccup, as the network instantly reroutes tasks and resources to compensate, ensuring that the exploration never stops. This is the profound paradigm shift from fragile, single-threaded missions to robust, multi-layered campaigns of discovery, where the combined power of these 28 tools will finally allow us to not just visit other worlds, but to truly know them. From autonomous rovers to fusion reactors, these 28 revolutionary tools are reshaping how we explore alien terrain, turning science fiction into science fact. Each innovation, from the microscopic precision of an atomic force microscope to the planet-spanning power of a quantum communication network, represents a fundamental leap in our capabilities. They are not merely incremental improvements, they are the keys that will unlock the next great age of discovery, allowing us to answer questions that have haunted humanity for millennia. Are we alone in the universe? What secrets do the icy oceans of distant moons hold? How did our solar system form? And what is our ultimate destiny among the stars? These tools provide the means to move beyond speculation and into a future of definitive knowledge, bringing us closer than ever to understanding our universe and our unique place within its vast, beautiful mystery. As we stand on the brink of this new era, it is vital to remember that these breathtaking advancements are not just for scientists and astronauts in labs and mission control centers. They are a testament to human curiosity, ingenuity, and our relentless drive to push beyond the next horizon. They belong to all of us. Every time a rover beams back a panorama from Mars or a telescope glimpses a new world, it is a shared victory for our species. These missions inspire artists, engineers, students, and dreamers everywhere to look up and imagine what might be possible. They remind us that the greatest explorations require the combined efforts of countless individuals, each contributing their passion and skill to a collective endeavor that stretches across generations and transcends borders. This journey into the cosmos is, at its heart, the most human of adventures. If this glimpse into the future of exploration has sparked your imagination, if you find yourself wondering which of these incredible tools will make the next great discovery, then you are already a part of this story. Share that excitement with others. Pass this video along to a friend who loves science, a family member who gazes at the stars, or anyone who believes in the power of a big idea. Let us know in the comments below which tool amazed you the most. Was it the resilience of self-healing materials, the incredible potential of fusion power, or the brave descent of a cryobot into an alien ocean? Your perspective adds to this ongoing conversation about our future in space. And if you want to join us for more deep dives into the technologies that are reshaping our world and beyond, be sure to subscribe to the channel. Together, we will continue to explore the incredible innovations that are turning our grandest dreams into